I'm going to start letting people in.
Welcome, everyone. I see people are still accreting. Numbers are still going up, so we'll just wait a minute before we get started here. Okay, so on behalf of the Gemini staff, it's a real pleasure to welcome everyone to the final day, day 4 of the Gemini Observatory 2021 Virtual Science Meeting. My name is Janice Lee, and I began serving as Gemini Chief Scientist this past March. And if you've been with us on any of the days of this conference, you know that we start the talk sessions with this virtual welcome to get everybody oriented and to help everyone get the most out of the Whova platform, which we're hosting the conference on, and from the program. So we made it. It's our final day, day 4. Today we have a time domain astronomy session, which will lead into a discussion of Gemini in the future over the next 5 years, over the next decade, and even maybe looking out further. To cap off the conference, we have open-ended panel discussion. The panelists are featured here. I think it's now in the Whova agenda, but we have Jen Lutz, Pat McCarthy, Myung-Chin Im, and Guillermo Blanc. This is also a reminder that after we wrap up with the panel discussion, we'll have a conference photo that is at 2:15 Hawaii time. Joe, did you want to say anything about that right now? I think the idea is
I think everybody will be asked to turn on their video, and we'll take a screenshot. We will take several screenshots because we can't fit everybody all in one panel.
Okay, thank you. And then after the conference photo, of course, we have the chat rooms and one last workshop, which we know will be attended because everybody is interested in data reduction. So that will cap off the end of the conference after the talk sessions today. Of course, it's been interesting to see how this Whova platform works in terms of encouraging interactions. And we've had at least a couple of chat groups formed. There's a plant photo group and a pet photo group. And today, or yesterday, Carlene Silva from the SOC started a group to talk about issues during phase 2 setup. So go have a look. It's on the Whova community tab. If you wish to talk about some issues that you've been having so that she can improve the documentation for those items or set up a group yourself. And just another 2 reminders before we get started. Each day we have chat sessions with the speakers, chat rooms. Please sign up to reserve a time slot or drop in to say hi, to ask a question you have about the talk they give. There's a Google sign up sheet that is linked to each instance of the chat rooms on the app. And also, as a reminder, I think most of us are accustomed to this by now, but likely there are new people joining us today. Our Q&A procedure is that there is an individual Q&A tab for each talk. And so you, in order to see the Q&A for that talk, you need to move between tabs, between sessions on Whova. But the Zoom link is constant. You can just stay here for the entirety of the talk sessions this afternoon. And if you have any problems, please go to Whova Community under the Ask the Organizers Anything group, or if you're having problems overall in general with the app, you can email us at the email address there, gemini21bsm@noirlab.edu. So with that, I'll go ahead and check to see if there are actually any questions on procedures or the program for today. Okay, and with that, so I'll introduce the chair for today. Oh, this was a reminder, actually. After the conclusion of the meeting, the LOC has put together a survey, and it would help us greatly if you could participate and give us your feedback on how you felt the meeting went, especially because this is our very first virtual meeting. So please look in your email in the next couple of days and help us make the next one better. Okay, now on to the introduction of today's chair. Today's chair is Jen Andrews, assistant astronomer based at Gemini North. She is part of the Science Operations Group. She helps observers with their phase 2 prep, and she is also goes ahead and helps you take your observations, take your data at the telescope. She is the contact scientist for most TOO programs, and she's also a member of the GMOS, GNears, Maroon X, GRACES, and Fast Turnaround teams. Her research interests are the evolution of massive stars, especially their deaths, which result in core collapse supernovae. So Jen, are you there?
I'm here.
All right, take it away.
Okay, great. All right, so thanks for that, Janice. So we'll be starting our first session here on something I know very little about. Let's see, Meg, are you sharing yet? I don't see it yet. But we have Meg Schwam from Queen's University Belfast, and we're going to be talking about many moons in the solar system and various other observations, a lot of which has been done with Gemini. So Meg, if you want to take it away, and of course, Jamika will let you know when you have 2 minutes left in your talk, and then we'll move to question and answers.
Great, thanks. I think you can all hear me and see everything. So I wanted to really make this a talk, really be sort of highlights in the past few years about why Gemini has been so great to do solar system science, and how both the flexibility and the large and long program really have delivered really unique science. And if I get time in the next few minutes at the end, really what's coming, because I think thinking about solar system in terms of time domain is really important. Okay, so I know this is time for something different. So why do we study small bodies in the solar system? What does that tell us thinking about planet formation? And so I like to think of the solar system really as the best exoplanetary system we will ever study because we're sitting in it, right? And so we're able to actually study the building blocks left over from the terrestrial planets and the giant planets that, and use that to study the compositional structure as well as the dynamical history within the solar system. And so it's not something we can yet do really on the same sort of scale in exoplanetary systems. And so there's really this nice thing of being able, if we can understand our solar system, how we can compare that. So I think a lot of what we're doing is still really probing those very fine details of our solar system's composition, both from the primordial disk and how it gets to what it looks like now, to what is really those inventory of those populations we know of. And just to give you some scale on this, right? This is showing the known inner solar system and outer solar system that we have today. And so all of these colored dots are minor planets sitting in the inner solar system, with these rings being the orbits of the planets. So you have Jupiter here, and then Mars, Earth, Venus, Mercury. And so again, just showing you the huge number of known objects, again, stealing this plot from the minor planet center, and showing you the outer solar system with these rings being giant planets. So Neptune, Uranus, Saturn, and Jupiter. And so again, showing you the sea of planetesimals. We know of over 4,000 Kuiper Belt objects or trans-Neptunian objects, and many, many more asteroids. And so again, both the sizes, the compositions of these objects, the distributions in terms of volatiles on their surfaces, their shapes, tell us a lot about planetary formation and the evolution of the solar system. And so Gemini, I think, has been really great in being able to probe in unique ways, pushing deeper, as well as being able to rapidly respond. So to highlight some of that, I wanted to give the context of why we want to study these and what things we've learned in terms of sort of understanding the unique dynamical properties of our solar system that sort of put these things into context. So one of the things is, from studying the outer solar system and even the inner solar system, we know that our giant planets have moved around. Stuff has moved around. Jupiter's moved inward, Saturn, Uranus, and Neptune moved outward. And that planetesimal scattering event emplaced objects into the dynamically excited population within the Kuiper Belt. So when we studied that, these objects with higher inclinations and eccentricities, we're really understanding about objects that were closer in, we think, and that the cold dynamical Kuiper Belt, we think, actually formed in place. And so again, by studying this region beyond Neptune, we're able to actually probe different parts of the compositional disk that no longer actually exist right today because the giant planets moved around, messing things up. And same thing if we look in the inner solar system, right? There's evidence to suggest that Jupiter and Saturn were in a mean motion resonance and migrated inward by, again, gas drag migration, and then move back outward. And so again, that sort of maybe probably cut off the feeding zone for Mars, but also sort of in place two different compositional types of asteroids, or at least this is one theory for that. And so a lot of what we're doing is trying to understand how this story, or these stories we're putting together, and these theories actually, are true, and testing them, right? And seeing how this works. And part of that is understanding how, in terms of what we've been doing, that, wide field surveys have been able to get us, larger objects where we have painted this picture, and now trying to probe to smaller sizes where we can see, and the devils in the details where we're getting with this. And so I should say, that what's been the work that I'm showing here, or will start showing, is from my postdoc in my group, Gregory Federer, who is now a Marie Curie Fellow at Queen's University of Belfast in my group. And so what he was working on last year was really focusing on understanding mini moons and this opportunity that came up to study 2020 CD3 with Gemini. And so mini moons are temporary captured orbiters. They're really tiny near the asteroids that are coming in, get caught into the Earth's potential well. And because they're coming so close, it means that we actually get a chance to view these very tiny objects with the ability to actually point telescopes at them and look at compositions and densities and sizes. And so within the asteroid belt, right, we can't actually see with current telescopes these very, very small sizes, the things on the order of, again, a few, 10 kilometers or smaller. And so the idea is that we're actually able to use this opportunity, although it sometimes lasts only a few weeks, where it's close enough to Earth to be actually imaged and also hasn't escaped yet. But the idea being using Gemini to be able to do that. So for 2020 CD3 came up, it's second to known mini moon that we've actually caught that while it's still in orbit. And before this, there was none that we actually had compositional data on. So we didn't know exactly what types of asteroids or compositional types we think these are from. And so the beauty of being able to use Gemini has really been able to do this rapid follow-up. And to give you a sense for scale for these very small objects, the boulders, this is an image of Ryugu and near-Earth asteroid Hayabusa 2 visited. These big boulders are about the size of what we think 2020 CD3 is. And so I credit to the Gemini North team, because this proposal went in on a Friday and on a Sunday morning. We had a phase 2 submitted, and by that evening in Hawaii, they were observing on the target. And so again, I think the credit for Gemini to bend over backwards to get interesting data. And so because of moving so fast, we got the compositional data on this object. And so here I'm showing reflectance versus wavelength for this object. And then the color bands are showing sort of the scatter for different compositional types within the asteroid belt. And so what is nice to see is that we can rule out some types of asteroids and that this looks like either an S-type or V-type. So V-type are chunks of Vesta. And so what's nice about this is it helps confirm that these very small, these meter class objects, at least this one, is consistent with what we see for larger near-Earth objects, which are that predominantly they're S class in composition, right? And so the idea being here is that we have this unique opportunity before this went away and got too faint to be able to look at the class and help compare to the models we think from where in the asteroid belt these mini moons are coming from. And so right now, based on identifying this as either an S or V type, we're able to say that this is consistent with what we see for the models, which are that about 40% of the population of mini moons are predicted to be S type. And so it's nice to see that we're with Gemini data where we have a first compositional class for this object, or at least we break it down to 2 classes and be able to test these models. And so with combining the Gemini data with the light curve and astrometric data, it was actually even, Grigori was able to, with collaborators, to come up with a density and a range of geometric albedos for this object. And so the density, depending on the type of the spectral type for this object, the composition, the surface composition, the densities are around 2.5. And then the geometric albedo is around 0.3, 0.4, and that's consistent with what we see in the asteroid belt. So again, right, really, we can't probe these sizes in the asteroid belt, but being able to sort of sample them as they come by Earth very quickly with the flexibility of Gemini and that queue scheduling and that rapid response, I think is really key to being able to study these. And so it's just what highlighted an example I wanted to highlight of how that flexibility in Gemini really came through and being able to get the first compositional characterization for a mini moon, given we only know of 2 that have stayed in orbit and a few that might have impacted that there is no compositional data on. The rest of my time, I really want to focus on talking about the other end of sort of the spectrum of Gemini and really highlighting the unique opportunity that the Large and Long program has been. So I've had the pleasure to be part of Colossus, which is Colors of the Outer Solar System Origin Survey. Wes Frazier is PI of this program and collaboration. And so I know he's somewhere probably on Huva or Zoom watching, but this is the core team sort of shown in this image. And so what Colossus does, it was a Large and Long program that then continued in Q programs to get compositional data for Kuiper belt objects to really try to understand the compositional dynamical map within the Kuiper belt. And so leveraging Mauna Kea, and so using Gemini and its fast switching ability to get R, G, J, GR observations. So getting R and G band and near infrared J observations of these very small Kuiper belt objects to really look at the composition. Plus getting U band near simultaneously with CFHT. And the idea really thinking about this is that in terms of understanding the Kuiper belt and the Trans-Newtonian region, most small Kuiper belt objects don't have the signatures of volatiles like the dwarf planets do. So we don't see signatures of methane and ethane or carbon CO. We basically see a flat spectrum in the optical near infrared that can be sort of measured as featureless spectra with basically a linear slope that we can look at. And so by getting R, G, and J, we've got enough to measure that slope and see any changes that might be happening in the spectra to identify unique objects, but also sort of try to map back to Neptune's migration where these objects were, particularly dynamically excited ones originally before Neptune's migration, and test this theory. And so this has been a uniquely challenging program, and I think it highlights that ability of Gemini and its flexibility because solar system objects rotate. And so it's not enough to get 3 filters on at once. We actually have to take out this rotational variation if we want to actually get the intrinsic colors. And so the trick with Colossus is to observe this object for several hours, each of these roughly 90 KBOs, switching the filters and then going into from GMOS north to NIRI. And again, that's not something that every telescope can do. So this is really uniquely only capable Gemini program. And so the idea here is that by switching through the filters and going from R, then G, then J, and then back out through the filter wheel and into GMOS, we can fit a linear line to the light curve variation for the object, plus simultaneously fitting the GRJ optical colors. And so getting G minus R and R minus J so that we can then map this. And also being able to take our Gemini observations and really push in the photometry by doing pill-shaped apertures, because we're tracking sidereally to be able to get the most out of our photometry and have our stars have good symmetric PSFs. So really, Wes and Mikhail and Marseille have really been pushed on all of the data analysis, and we now have a really nice set of photometric colors to play with. And I should highlight what makes this sample unique, above and beyond the observing, is really thinking about where the sample comes from. And that's really thinking about that this came from the Outer Solar System Origin Survey, all of our 96 objects taken from a brightness limit cut. And that means because the survey has well-known detection biases, we know every object that we have colors on from Colossus, we know what's the likelihood of finding that object in ASOS, which means we can go back and really take the survey simulator for detections for the survey plus our colors to really start probing the dynamical history within the outer solar system, as well as answer other questions. And so one of the things we wanted to do in taking this from the proposal was, looking at Neptune's planetary migration and what happened at the end stages. And so depending on how Neptune sort of ended, whether it jumped or it was a very sort of smooth roll at the end, different objects got swept into different places within the Kuiper belt that we might be able to see. So let me just show you quickly the current Colossus sample and just show you what this roughly 90 objects look like. And there's some substructure in here, but really we sort of divide in broad terms, and there may be new ways to look at this data as we play with it, is that there's sort of a red component and a neutral component, or red and less red, depending on how you want to call it. And that we can look at fractions of these. We can also look at the substructure, all this kind of stuff now that we have this, plus high precision photometry. So this is the highest, this is the best error bars on photometric data for objects of this size, which are again 100 to about 300 kilometers. And so I want to highlight the Colossus results that are coming, but we already have 8 papers that come out of this sample and subsamples before this full release, and at least 2-3 papers that are in the work. So really being able to get this data set has done a lot. I want to highlight some of these works. Again, this is really just, I feel like in 20 minutes, I can't say a lot. So I want to advertise some of the key results that come out of Colossus, but really all of them I think have been incredibly interesting. So Rosemary Pike published paper in 2017, taking the Colossus sample plus some additional Z-band data we were able to get with near simultaneous observing with Subaru and Gemini, plus also getting additional Z-band observations on Gemini when we were in our visitor observing mode and actually had really good seeing, where we could reduce our exposure times and sub in some Z-band. And what we see here is that there does seem to be that depending on your dynamical class, we can separate out those objects. And so the first time this has been seen, that the cold classical objects, the objects that we think formed in place, sort of seem to cluster in G minus R, R minus Z separately than the dynamically excited Kuiper belt objects or surfaces, which seem to have, again, that sort of red and less red sort of splitting, but the cold classical seem to come out here on their own. And so this is sort of the first time in a way, without having the near infrared, that we can potentially pull out the cold classicals, which I think is really exciting for thinking about how we can use room observatory and other data sets without having to take the costly J-band. Another unique, I think, observation has been sort of doing comparative planetology. And so again, really thinking about what we can do. Go back. what we can do with interstellar objects. And so again, by having a large sample, we can compare to things that are coming into our solar system of similar sizes or smaller. So Oumuamua was the first interstellar object. Again, it's a planetesimal formed around another star, kicked out, and came falling into our solar system temporarily before it went on its merry way out. And so we were able to get director's discretionary time with Gemini, and Michelle Bannister led this paper and proposal to get the same kind of Colossus observations we get on Oumuamua so that we could compare it. And so this is what this paper is showing, and this plot particularly. And so what I'm showing here is G minus R versus R minus J. And so the sort of blue points here are early Colossus data plus sort of all other data we could gather and put on the plots. And here's Oumuamua. And so, although if I had not told you what that star was, that red star was, you would have said it kind of looks like other solar system objects. And so we are, I believe, the only near infrared sort of color for Oumuamua. And I think that this is a really nice way of and that the Colossus sample itself now, nearly complete, will be used when we find other interstellar objects to be able to look at that. I want to just highlight briefly that my student, Laura Buchanan, has been taking the subset of the Colossus sample and really looking at how you can take this to sort of probe that migration of Neptune. And so she's taken a couple of the observing blocks or samples from Colossus and looked at and splitting them into between that red and blue class and seeing what happens in dynamical models for Neptune's migration if you take that disk and then you observe that simulated Kuiper belt through the outer solar system origin survey and then observe Colossus. Knowing that these objects have been labeled either red or blue, can you actually see whether red surfaces or blue surfaces should, whether the ordering in the primordial disk matters. And so preliminary results
we're
from
running,
the work she's been doing.
We're running to the end here. So if you could just go ahead and quickly wrap it up.
I'm on my last, yes, I'm working on my last two slides. Don't worry. So what I want to highlight with this is that we're finding that you don't see the difference between red or blue for this. That if you have the red, then the blue, or blue, then the red in that primordial disk, you will be able to, you get the same sort of distribution. So that's already interesting. And so what I'll end in my last sort of slide is that the Rubin Observatory is going to find 5 million solar system objects and 1 billion observations of them. So an order of magnitude more solar system objects than ever before. And so with the monitoring from Rubin Observatory and that it's going to observe the sky every 3 nights, what we talk about transients now, I know everyone thinks about astrophysical transients, but the solar system is going to have that as well, because we're going to have this unprecedented monitoring, both for Kuiper belt objects and centaurs and inner solar system objects and comets. And so I just want to highlight this, that, all the fast flexibility in these large programs that Gemini has been able to do, I think is going to make a huge dramatic impact on follow-up that comes out of Rubin Observatory and LSST. So thanks for letting me take you through a little whirlwind tour of the solar system.
Great, that's awesome. Thanks, Meg. So I'm looking to see, I don't see any question answers. So please, if you have questions for Meg, put them in there and we can ask quickly. If not, the chat session, the session will stay up so you can continue to ask questions. I have a question. So these mini moons, what size are they? Are they like school bus size? Are they like more like stadiums? How big are we talking?
Boulders.
Okay.
Literally boulders. Very tiny.
So only through very large telescopes would you be able to detect them?
And very close, right? So it's the combination of the two. Yep. So even still bound to the Earth, if they go at their apogee, they might not be seen. So it's a few weeks at most in some cases, or even a day to observe them. So with Gemini North observing this mini moon that it was able to get, I think there was only about a week window where it was even doable before it would have been too faint.
Awesome. Okay, let's see. And I can definitely appreciate the the Vera Rubin mapping solar system objects, because as someone who looks for new transients, we are constantly finding moving objects in solar system objects in our fields of view, and we have to classify them. So being able to quickly tell a new astrophysical transient versus a moving solar system object will be fantastic. Let's see, any other, okay. All right, so Janice would like to know what would the priority in solar system follow-up be in the next decade with Rubin? What are you most excited for? What's the highest priority there? Is it Planet X?
I mean, Planet X, but well, I think Planet X is one, but I actually think it's the time domain. I think Rubin's going to find tens of interstellar objects, and each one tells us about composition of planet formation in other solar systems. So getting on that rapidly before and trying to see how they evolve, because we have two interstellar objects and they behave differently. Oumuamua didn't have a big coma, Borisov did. And it looks like the composition, at least the coma composition, appeared to change. And so I think that's really key in that rapid follow-up. I think also we'll be able to watch objects break apart, comets flare up. And so I think there's a lot of time domain that we've never been able to observe because we haven't had that capability of a wide field survey coming back so frequently. So I think that's sort of my exciting bit is how do we, when we find an interstellar object 3, 4, 5, 6, 7, I think that's going to be pretty exciting. But yeah, finding really distant comets or any kind of solar system transient, I think we'll actually really see large numbers of them. And whenever you have that much data, you're going to find something weird. So again, I think that's the exciting bit is how to figure out how best to trigger on the unique objects we might not have been expecting.
Awesome, thanks. So we are out of time. And so if you could stop sharing and we'll let Eleonora start sharing. But if you have additional questions for Meg, please put them in the Whova and ask away. And thanks so much, Meg. Great. All right, I can see you and I can see your talk. Perfect. Okay, great. So we are now moving out of the solar system and we are going to have Eleonora Trujillo here from the University of Maryland and NASA Space Flight Goddard to talk about GRBs and Kilonova and all sorts of wonderful things, a lot of which are being done with Gemini here. So take it away, Eleonora.
Oh, okay. Hi, everyone. Thanks for having me today. So let's start. As you said, I will talk about the search for Kilonova, which has been done with a lot of instruments, including Gemini. To start, I just wanted to show why do we care about Kilonova. So these Kilonova are a new type of transients that really became popular in the last few years. They are relatively luminous, visible mostly in the optical and infrared, and they're quite short-lived. So they really rise to the peak luminosity in a few days, and then they fade away really quickly. And the reason we care about them is because we think they are the signature for the production of heavy elements. So we want to study Kilonova to really understand what's the cosmic source of our process elements. But there are also the reasons we want to study Kilonova together with gravitational waves to improve the constraints on cosmology and the expansion of the universe. And we want to study Kilonova because they are connected with the collision of neutron stars. And so they really help us to probe the equation of state of dense matter in really cataclysmic and extreme conditions. So there are a lot of interesting astrophysical aspects related to Kilonova. There are also several ways to find Kilonova. I will start with channel number 1, which is also the channel that allowed us to discover the first Kilonova in 2017. That is the follow-up observations of gravitational wave sources. And as you see here, that is quite challenging because gravitational wave sources really span a large area of the sky. So it's a really challenging search. We were very lucky in 2017 because we found Luminous Kilonova event at only 40 megaparsec. What you see here in this plot are the light curves of this kilonova in different colors. And you see that it starts bright in the optical, but then it really fades away rapidly. And then the spectral peak moves toward the infrared band. And it stays there for a few days, and then again, it fades away in a matter of weeks. And so what we think happens when these two neutron stars collide is that there are a lot of outflows being ejected by this violent collision. So you see here, one of them, this orange one, is a beam of relativistic ejecta, and we think this beam produces gamma ray burst. But there are also these outflows here in blue and red. And we think the kilonova is actually related to these outflows of neutron-rich material, which are moving at a very fast speed, something like 30% the speed of light. And so what we see as kilonova is actually the emission from these, the mix of these different outflows. So to start, I mean, this is like the groundbreaking result obtained in 2017. As you are probably aware, we were not very lucky in the past year with the results of the O3. I mean, there were a lot of excellent results, but not a joint electromagnetic gravitational wave detection. I just wanted to discuss that despite the lack of a joint detection, we still were able to extract some interesting results from the search of kilonova from gravitational wave sources. And what I'm showing here is the latest announcement from LIGO of a neutron star black hole merger. This is really amazing because we thought that this neutron star black hole system, they had to be there, but we never had the evidence for their existence. And so what you see in this map is the localization of the event. You see this is a very broad localization spanning 600 square degrees in the sky. And what is even worse, it's you know, split between the northern sky here and the southern sky here. So what we do when we search for kilonova, we use this wide field of view telescope, and we try to cover the entire area of the gravitational wave localization. This is an example of what we did with the Dotti telescope. What you see here is a summary of many facilities that were involved in the observations of this you know, remarkable event. And you know, what you can see immediately is that unfortunately we need to trade field of view with sensitivity. So the instruments that usually manage to observe a large area of the sky do not have the sufficient sensitivity to probe the range of kilonova luminosities, and the one with sufficient sensitivity to probe the kilonova range you know, still did not cover a large area of the sky, something like between 20 and 25% in this case. Another example, again coming from O3, is this event known as GW190814. The reason I wanted to highlight it is number one is because in this case, the localization was much smaller. So as you can see, with a few tiles, we were able to cover the entire area. So in this case, there was full coverage. What you see in the zoom in, these are the locations of all the possible candidates found for this event. And the reason this event is also so peculiar is because we don't know exactly what it caused it. It could have been a neutron star black hole merger with, being the neutron star, the most massive neutron star ever detected. It could also be a very peculiar form of light black hole. So electromagnetic observations did not find a counterpart. What I show here is, the result of the follow-up from the entire community. So once we find all these little dots, these are our candidates. We really need to identify, not only to detect them, we need to classify them. And to do that, the contribution of large telescope is fundamental, especially for spectroscopy. And you see here in this pie chart, I report the status, and you see that 1/3 of all the possible candidates was excluded and ruled out because of spectroscopy. So it was either classified as a supernova, or the distance scale was not consistent with the distance scales of the gravitational wave event. And the other were ruled out because of they were present in archival images, and other were ruled out based on the photometric and color evolution. And there is only 1/4 of the event that remained unclassified. One thing that I wanted to point out is that this 25% is mostly composed by candidates that were announced with several days of delays. So it was remarkable how most of the candidates announced within a few days after the gravitational wave follow-up were somehow classified by the community. And so this really shows how, the rapid identification of transients and their rapid follow-up observation is critical in this field to really achieve the main result, which is the identification of the gravitational wave counterpart. Okay, so here just to say we did not find the counterpart, but we still placed meaningful constraints. So what you see here in this plot is the range of models that we can rule out. You see there is a wide range that unfortunately is not constrained by the observation, but we can say that kilonova as bright as the one detected in 2017 is mostly disfavored. You see, is in this dark area where it's unlikely that it was there without being detected by this very intense follow-up. And just to summarize the results on a tree, these are all the limits we collected for the gravitational wave detection. They are compared with the expected peak magnitude of different kilonova models. And we can immediately see from this plot that the more sensitive the gravitational wave detectors become, the more distant these sources are going to be. So we are going to be dominated by binary black holes, from which we really do not expect a kilonova. There are here in O3, we had a few cases at a distance between, I would say, 150 and 350 megaparsec. And these are the events with a probable neutron star component, and these are the events from which we expect a kilonova. And what we learn is that these distance scales, most wide field imager would not be able to probe the full range of kilonova luminosities. That is something that it could be done with the Vera Rubin observatories in the future, but with current instrumentation, we can still probe the most luminous scenarios, like the one from, for example, a magnetar-driven kilonova emission, or for example, if we have a neutron star with a black hole that is highly spinning, we also expect a luminous kilonova component. And so this is within reach of current facilities and hopefully can be probed in future LIGO runs. And now I would like to switch to the other channel of kilonova search, and these are short duration gamma ray bursts. For people that are not familiar with them, these are like sudden flashes of gamma ray radiation, and we find them everywhere in the universe. Their distribution in the sky is isotropic. We cannot predict when they will happen, and that's why we have this SWIFT mission that really scan the sky and alert us whenever a short gamma ray burst is localized. And so why do we care about short gamma ray burst? The reason is, first of all, they're much better localized than gravitational waves, so the job is much easier, and we can use large telescopes like Gemini, which have a narrow field of view but a much greater sensitivity. And so this really allows us to explore the neutron star mergers and their kilonova up to higher distances. And so hopefully we're going to detect more. Also, as you see here, what happens is that the neutron star mergers are really asymmetric systems. And so when we use the short duration gamma ray bursts, we preferentially probe this direction that is along the rotational axis. So we preferentially probe a direction that is not probed through gravitational waves. So here is an example of how a kilonova looks like in a short GRBs. We see there is this component that we see both in the infrared and at X-ray wavelengths. This is the non-thermal emission coming from the relativistic material and not connected with the kilonova. The kilonova actually appears as a bump after a few days since the gamma ray burst. And so you understand the main challenge here is to really have observations that are sensitive enough to resolve this bump from the underlying non-thermal continuum. And this is where large telescopes in tandem with HST and in the future James Webb will be key to detect more of these explosions. I also wanted to highlight one case where we used the Gemini to discriminate between models and break the degeneracy. This is a recent short duration gamma ray burst. And in this cartoon, you see we detected this infrared emission that is quite bright, much brighter than the kilonova detected in 2017. And that was really intriguing. One possibility is that this extreme luminosity is powered by a magnetar. Another possibility is that this is a standard kilonova, with just appearing more luminous because we are seeing down the axis of the neutron star merger. And so for viewing effect, it just appears more luminous than it was in 2017. And as you can see here, these two models look very similar in the infrared band, but they differ quite a bit in the optical domain. And so we were able to place this upper limit with Gemini, which was quite deep, and this really allowed us to favor one model over the other one. Here is another example that is less cartoonish and more physical. So you see here, this is the model of a standard radioactive powered kilonova compared in blue with the magnetar powered model. And you see the degeneracy happening in the infrared band, and the rapid optical observation from large telescope are really critical to test this scenario. So this is a summary of what we have learned so far from short duration gamma ray burst. We have definitely a few more candidate kilonovae coming from the short duration gamma ray burst sample, but it's also true that we've been observing them for over 15 years. So it's definitely challenging to find them because of the large distances of short duration gamma ray burst. You can see here that all our candidates are events that are relatively nearby, definitely below 0.5 in redshift. And also you can see that the masses of ejecta that we can probe through short duration gamma ray bursts are quite high. So this is a 0.1 solar masses is at the very limit of what a neutron star collision can possibly do. And likely, if there is anything fainter, we are missing them with the current strategies and instruments. So just to look at the future, what we learn is that, using the current strategies to find kilonovae, the progress has been, both amazing because we got great results, but also challenging. We learned that not all the kilonovae, not all the neutron star collisions look the same. So we should not assume that every single event is going to look like the one we detected in 2017. We learned this in 03, where we did not find any counterpart, but we could roll out several events with meaningful constraints. For the future, I mean, we expect a higher number of events with smaller localization. So hopefully we are gonna get more chances to search for kilonovae, but we should also keep in mind that these events will likely be more distant. And so it's going to be the help of large telescope to weed out the candidates and classify them is going to be really fundamental because they're not going to be very bright. The other channel that we use so far is discovery of short duration gamma ray burst. This channel has been quite slow in progress because just we have a few of these short gamma ray bursts in the nearby universe. And so hopefully with James Webb, we will be able to probe the existence of kilonovae up to a much higher redshift. So we will have just more chances to test the kilonova model in gamma ray bursts. And finally, in the next few years, we should be able to add another channel of detection, which is just the serendipitous discovery of kilonova through wide field surveys. So without gravitational waves and without a short duration gamma ray burst, we might be able to just find these unusual transients by themselves. So these observations that we're doing now will be very useful to guide this effort for future surveys. Thank you.
Great, thank you, Eleonora. So there are, let me refresh to see if there are any questions. None have shown up yet. So I get to use my my chair question for you. Is there any particular, if you had to pick a wavelength range, is there any wavelength range which is the best to have to help distinguish the kilonova, or do you really need a full-on multi-wavelength campaign to decide if it's a kilonova or not?
Well, if you do infrared spectroscopy, I think that would be with James Webb, that could tell you if you have a kilonova. Just looking at the spectrum, you could detect the features. But my experience that they're so rare, like even in the future using wide field surveys, these are going to be rare events. We're not talking about 100 per year. We're talking about a few per year. And so I would throw everything at them just because we need to extract all the information available. And models have degeneracies that really require multi-wavelength observations to be discriminated.
Right. Okay. Awesome. Okay, good. Well, there aren't any other questions, so I have one more for you. Why was it that in 03 we weren't successful? Is it just the distance, or I know we were super lucky with how close 2017 GFO was, but we did expect to at least see one. And so was it that that none happened, or we didn't detect them, or we didn't follow up quickly enough, or have the coverage we needed? What do you think is the biggest issue there?
Combination, but probably the localization was our biggest enemy. As I showed, in some cases we were able to place constraints, but just for like 20% of the total area. So we don't know about the remaining 80%. And in some cases it was even less. So having a smaller localization, I think it would be critical.
Wonderful. Well, thanks so much. And if anyone has any other questions for Eleonora, please put them in the Whova and that'll stay up so we can keep chatting about those. So now we can move on. If you would like to stop sharing, Eleonora, then we'll hand it over to Monica, who is going to sort of build off of Eleonora's talk and discuss the future of time domain astronomy at Gemini. Great.
And can you see my slide and hear me well?
Yes, we can. Great. So Monica is you're a researcher, correct, at University of Illinois? Yes, but yes. She will be moving to Gemini soon. So welcome. And go ahead and discuss, give us a future update of what we can expect over the coming years.
Thanks, Jen. Okay, so in this talk, I will describe the current time domain astronomy landscape, which is being shaped by a surge in data, and highlight the niche that Gemini will occupy in that landscape. But first, here's a brief overview of the evolution of time domain astronomy. So the growth in this field has been propelled by the application of photography and CCDs. And here are some notable results from this field, which include the discovery of the Cepheid period luminosity relation in the early 20th century. Then from the late 1990s, we have the first detection of a microlensing event and the Nobel Prize winning discovery of the accelerated expansion of the universe using high redshift supernovae. And then, of course, from the last decade, we have the discovery of superluminous supernovae. And most recently, time domain astronomy has gained increased significance with the search for electromagnetic or EM counterparts from other cosmic messengers, like gravitational waves and neutrinos. The left plot shows the detection of the famous Kilonova counterpart of the gravitational wave event 1708-17 that we just heard about. This was promptly detected in less than 12 hours following the LIGO trigger. Then on the right-hand side is the candidate EM counterpart of a high-energy neutrino, which was detected by the Ice Cube Observatory in Antarctica. This tidal disruption event, AD 2019 DSG, was found to be spatially and temporally coincident along this dotted line in its light curve with that neutrino. Now, if we talk about data analysis, time domain astronomy has conventionally relied on visual comparison of images, like this discovery of Pluto by Clyde Tombaugh using the blink comparator instrument shown here. But of course, with the modern data rates, visual comparison, visual inspection is out of the question. And of course, we've got computers to do that job for us. So the detection process in present-day surveys is entirely automated via the difference imaging analysis procedure, where a new image of a field is subtracted from a deep coed of the same field called the reference, generating a difference image where the varying sources, they show up as positive or negative flux excursions, like this one here. And we call these varying sources as alerts. Now, automated processing also comes with its own issues. Some of the important ones include the contamination by artifacts of the differencing process, and also trying to identify the astrophysical sources of interest from the huge volume of detected alerts. Our community has adopted machine learning classifiers to solve some of these issues, and that seems to be performing quite well. Now, to set the stage for the real-time challenges, here is the figurative comparison of the data rate in our field decades ago in the left here, and the data rate now and in the near future. And an important source of this data surge in the immediate future is going to be Rubin Observatory's Legacy Survey of Space and Time, LSST. This broccoli image here was snapped by the sensors of the LSST camera as a test shot. And as you can see, its field of view can fit about, I think, 40 or so full moons. And here are the expected numbers for its data. So we're going to receive terabytes of imaging data per night, which will generate up to 10 million alerts every single night. And there will be several hundred petabytes of data over its 10 years of operation. But on the other hand, based on current status, just around a few tens of sources can be followed up per night. To get more sense of this time criticality, here is the distribution of the optical peak magnitude of extragalactic alerts detected by the Zwicky, the ongoing Zwicky Transient Facility, or the ZTS survey at California. The sensitivity of this survey drops off at around 21 meg or so. Veritas supernovae are included in these alerts. And more than half of these sources, they have got their peaks fainter than around 18 mag. So if we are to do, like single one-time follow-up observation of these sources, this is a rough sketch of the aperture requirement. I've assumed pretty generous integration time of an hour or so for spectroscopy, shown here in blue. At the faint end, we would have to settle for low-resolution spectroscopy in the form of simultaneous multi-band imaging, which can be done with any, I think, mid-size or small size aperture telescope. But then this is just the peak of the events. And what we typically want to do is to trace the evolution of these sources to investigate their underlying physics. So for example, these two light curves are those of fast blue optical transients, or FBOTs. In the top panel is the famous 80-20-18 cow, or simply the cow. And in the bottom panel is the light curve from a recent event called the koala. The nature of this FBOTs is still unknown, but they seem to involve some strong energetic shock in a dense medium. And as you can see from this plot, these events, they decay by like 1 magnitude in a day. And what we're interested in is getting such a sequence of spectra, like shown here for the cow, covering, I think this covered about 2-month time in its evolution. So the time axis increases along this direction. Majority of these spectra have been gathered by GMOS on Gemini, particularly at the later epoch, when the event had significantly faded. Now, studying the development of these spectra, it gives us the clue to help unravel the nature of these events. The koala was unfortunately more distant. It was a redshift of around greater than 0.2 as compared to the cow, which occurred in a galaxy just 60 megaparsecs away. So this one peaked at an apparent mag of just 19.5. And so only one optical spectrum was obtained at the peak, and new late time photometry was obtained, which therefore prevented from a complete interpretation of this event. So the takeaway here is to uncover such and other short-lived astrophysical events from the torrent of alert data. Specialized infrastructure and data mining algorithms will be a necessity. So for present and upcoming large-scale surveys, this ecosystem is going to be the standard for doing real-time science. So taking LSST, the survey data will flow to its data center, where a huge number of alerts will be generated and distributed with a latency of around 1 minute. Those alerts will be ingested by software instruments that we call brokers. These brokers will sort through these alerts to identify the high priority events, and then will be distributed to the community near real time to allow rapid follow-up. Follow-up will be facilitated by software tools such as the Las Cumbres Observatory Stargate Observation Manager that Brian gave a nice intro in yesterday's workshop. Now, observations themselves, the observations should be ideally conducted by a coordinated network of facilities like like that of AEON, where Gemini is going to provide the largest aperture there. Brian will talk more of this part of the ecosystem in the next presentation. So, observations are gathered for these events. Those data will flow to the scientists who will, analyze them, make discoveries, perform characterization, and perhaps feedback to the brokers to improve the filtering functionality, or they may trigger further follow-up observations. And lastly, these brokers, they are sophisticated enough that they can trigger follow-up automatically using the TOM tool if required. So to specifically focus on Gemini for time domain alerts, it's not just the aperture size that it's got to offer, but this whole suite of instruments that we've heard about throughout this week. So covering from the spanning the visible all the way to the mid-IR. And with the development of Scorpio, the single instrument covering both visible and near IR, and to be used for dedicated LSST follow-up, this facility will be unmatched and a game changer in the follow-up ecosystem. But again, it's not just the instruments. So for real-time applications, the turnaround time from observations to reduce data is also equally important. And on that front, of course, Gemini has the Dragons program in place. And I think Kathleen is demoing this later today, so do check it out. Okay, in the next few slides, I will focus on the broker for timely discovery of interesting sources, in particular, NOIRLab's own Antares event broker that I have been involved in the development of. We are also one of the selected brokers for LSST alerts. So Antares has been processing the live alert data from the ongoing ZTF survey, whose alerts are generated at IPAC at Caltech and are being streamed to the community via a Kafka server hosted at the University of Washington. Antares ingests these alerts, processes them, and the filtered output are delivered. The outputs are delivered to the community via multiple services, which include Slack. And we've got a Python client library for anyone wishing to subscribe to the real-time, to the filtered output in real time in bulk. We also have a development toolkit for archival search of our alert database. This can be accessed via NOIRLab's Astro Data Lab service. And finally, we also have a web portal. Okay, so from ZTF, we have been receiving about a few 100,000 alerts per night. And in 14 months, we received a total of 10 million alerts, as is shown in this sky map. And I wanted to highlight that number because that's what's projected for LSST on just one single night. You can access our flagged ZTF alerts on this link here, antares.noirlab.edu. We also have an integrated target observation manager, which has been set up at this website. So for our team, we don't need to set our own TOM. And this is thanks to the effort led by my colleagues, Chansu Lee and our software engineer, Nick Wolf. Currently, this TOM is tied to the observing time granted to our team. So when you access this link, you won't be able to trigger on an alert, unless, of course, you're ready to share your time with us. However, Chansi has also written this really nice tutorial on using Jupyter Notebook to build your own TOM and trigger on an Antares alert. If you're interested, please do check out this link. So since Antares went live around the end of 2018, we have flagged many interesting sources. This table shows some data we have published from those flagged alerts, which include various types of supernovae, dwarf novae, and novae. There are additional interesting events we are currently following up with our collaborators. If you're interested, I'll be happy to share details offline, maybe during the chat time. We have more results like this ARC or BOR, which was found by our team by just mining the Antares archival alert database. We have also been developing an algorithm for finding anomalous events. I won't go into details, but if you're interested, please do ask me later. So applying this algorithm to the ZTF alerts in real time with Antares, we have obtained many interesting results, like this huge amplitude precursor event in the rare WZSGE type dwarf novae that has never been observed in dwarf nova of any kind. I'm going to skip the slide. Additionally, our team is also working on setting up more formal classifiers beyond the broad filters and community contributed classifiers that we have been running. Here are some preliminary results. The left plot shows the absolute magnitude distribution, the peak absolute magnitude of extragalactic transients flagged by a filter on Antares. So at the brightest end, we have the AGNs, then various types of supernovae here. Then at this region are the intermediate luminosity optical transients or ILOTs. And at the faint end are the novae and variable stars in nearby galaxies like Andromeda, M33, and so on. The right-hand plots, they show the characteristic timescales along the x-axis and amplitude along the y-axis extracted for these events. For the G band, R band, the G minus R color curve, and this plot shows the ratio of the ratio of the timescales in the two passbands and the ratio of the amplitudes in the two passbands. Now for individual passband plots and the color plot that you see here, there appears to be at least two overdensity regions, as is shown by the contours. And I can tell you that one of the groups is the supernova group, and the other is the AGN group. I've tried to use these timescales and amplitudes in a tree-based classifier, which I'm calling this model as NTFI first generation. I've supplemented these features with a few more extracted contained in the alert metadata, and those sensitive to the shape of the light curves. And here's the confusion matrix resulting using just 16 features for the extragalactic transients. And this result is comparable to what is obtained by the Alerce group, which is another broker based at Chile. And theirs is based on 150 plus features. So I think it's a pretty nice result. So finally, to summarize my talk, the biggest challenge, I believe, for modern surveys in the optical domain is the data volume, and particularly the data rate. So for real-time science, end-to-end automation from observation through reduction of the follow-up data will be essential. And in the LSST era, Gemini will be at the forefront to explore the faint uncharted parameter space. Thank you.
Great, thanks, Monica. Let's see. So Janice has a question, and she would like to know what distinguishes Antares from the other Rubin alert brokers.
Yeah, that's a great question. So we have or rather like one particular feature that is unique to us is we allow the community to run their own custom filters. So anyone can, we let the community decide like what is of interest to them, right? So they can write their own filters, and we will run those filters for them in real time on our platform. And this has not been implemented in any of the existing brokers. Additionally, we are, so as I've shown in my presentation, we stream this filtered output via these multiple services. I believe the rest of the brokers, they are utilizing just a web portal. But in our case, as you're also aware, we've got the Slack the notification system. Then we have this client library where one can sort of receive the filtered output from the submitted filter in real time.
Great. Yes, and I have used these filters, and they're great to especially keep an eye on specific variable stars or things that you want to have an alert for in case it decides to get brighter or fainter. Which leads to actually the next question by Clara is can you explain how Antares can distinguish between, say, pulsating variable stars, AGB, supernovae, Since
That's
it is just a light curve monitoring thing, yes.
Right. So right now, what we have is sort of like a hierarchical, separation of the groups. It's pretty easy to separate variable stars, well, relatively easy to separate variable stars from transients like supernovae, AGNs as well, because there are some metadata information that helps contained within the alert packet that tells us that something is extended and something is not. In terms of, so after this separation, if one is specifically interested in variable stars, we don't have a filter to do the class separation between the various types of pulsating stars, Lyrae, Miras, and so on. But as I showed you, this classifier that we are building, which is currently for the transients class to segregate the different types of supernovae, we are going to expand that to do the classification for the variable stars as well.
Awesome, great, yes. And that's sort of, I just have one more quick question and that's sort of tacking onto this. So the plot you showed with the number of events versus magnitude, there seemed to be between -15 and -20, a whole bunch of different objects that sort of overlap there. Is there any way to really tease those out without spectroscopy or individual follow-up?
So with ZTF, from this analysis, my conclusion is it's impossible. But but with spectra, of course, definitely. But if we are starved of spectroscopic observations, then I believe additional past observations from additional past bands that may help. So I'm pretty excited to see how this classification, this clustering will work out when I incorporate additional past bands, maybe from Rubin, for example. So.
Awesome. Well, thanks so much, Monica. And we are at the end of our time, so we'll move on to our next Gemini talk. So Brian, if you are there and would like to start sharing. So I imagine many participants met Brian yesterday, but now he's going to discuss the next generation of time domain astronomy with Aeon and TOMS. Let's see, is Brian here?
He says he can't share. Jamika, could you check that he's a host? And
okay, now he's a co-host.
Yes, just made him co-host.
Great.
Great, thank you.
Okay, wonderful. So we can see.
Okay, that looks, everyone see that?
Yes.
Very good.
Great. Well, take it away then, Brian.
Okay, thank you. So as you've seen from the recent talks, that Gemini has always done a substantial amount of time domain astronomy due to its sort of dominant Q mode. And as you can see in this plot here over historical use of Gemini, about 20-25% of the time charged in band 1 goes to TOOs. So that leads to a max TOO rate of 1 or 2 a night, unless we have a Kilonova where everyone wants to observe the same thing. Unfortunately, the process is rather manual and not as efficient or capable as it could be. And in this new era of time domain surveys like ZTF and Rubin LSST, multi-messenger astronomy, we must be prepared for a higher rate of TOOs and just do the ones that we get more efficiently and more capably. So improvements are currently underway to attain our strategic goal of being the premier TO follow-up facility while continuing to protect and enhance the non-TO research that all of us do. So to put this in context, I'd like to show another version of the time domain follow-up system. So as Monica showed, we have facilities doing surveys or doing alerts like LIGO. The alerts are collected in the brokers, such as Antares, which do the cataloging and the classification. And then the science team sit here in the middle using these TOMs to collect the filtered alerts that they are interested in from the brokers, and then submit observations to the facilities on which they have time. And that takes us to the EON network. And so I'll be focusing mostly on the right part of this diagram here. Now, an important part of the facilities, is the instrumentation that you'll be able to use. Monica went over a little bit of this, but I'd like to emphasize that almost most of the facility instruments that we have can be used for TOL follow-up, but it's the workhorse optical and infrared instruments that will be the most useful, the most used, because they're on the telescope most of the time. Again, we can mount 3 instruments at a time, but we usually have like 2 on most of the time and then switch 1 other port. So we've had a lot of good talks at this meeting about the future instrumentation. So this slide tries to give one option for instrument suite in the mid-2020s. So in Gemini North, we've got GMOS North and GNIRS would probably be the most commonly used instruments. In the South, we have GMOS South, Flamingos 2, and as we heard yesterday, Scorpio, which is under construction and is designed specifically with this wide wavelength coverage to be a TO follow-up machine. Just one thing to mention is that you can do TOs with the AO systems, but you need to submit your trigger a few days in advance so that we can go through the laser clearinghouse process. Now on to a little bit more about what these TOMs are, target observation managers. It's basically a web interface on top of a database, which allows you to pull in targets from these brokers or upload them from a catalog, do your prioritization or analysis, and then submit observations to the facilities on which you have time. And then download the data. It can help you process the data and figure out what to do next. So these traditionally have been used by a lot of different time domain projects, supernovae, exoplanets, microlensing, but they're also useful for non-TDA projects. Anything where you have a lot of targets or you have a large team and you need to manage access, these are also useful for that. And fortunately, the Las Cumbres Observatory has developed this toolkit, the TOM toolkit, which makes it very easy to set these up. I showed in the workshop last night that you can put one of these together in under 15 minutes. So check out that if you want to learn a little more about how to do these. So once you've got the observations submitted to the facilities, we need to be able to observe them efficiently. And that is why NOIRLab and the Las Cumbres Observatory are collaborating on the EON, which is the Astronomical Event Large Observatory Network. It's basically an effort to promote this little network of programmatically accessible, dynamically scheduled telescopes. And the main goals of this project are to develop the interfaces that are needed internally and externally, use SOAR as sort of a pathfinder, which uses the LCO scheduler to feed Q on dedicated sort of EON nights, and that's working right now. We're encouraging data pipelining and archiving, incorporating Gemini, investigating TAC processes so that we can use this efficiently, and then be ready to incorporate other facilities like the Rubin in-kind contributions or the Blanco as when the time is appropriate. So as I mentioned, we're working on discussing TAC processes, especially between this EON working group, which is helping to set this up, and the Gemini board, so we can make the best use of this system. The aim that we've had is to try to make it as easy as possible to apply for the multiple facilities and reduce multiple jeopardy, but we also need to meet participant requirements for proposal evaluations. So the concept that we've adopted is as follows. All Gemini proposals will go through the Gemini NTACs as they do now. But if you need to use facilities that are allocated by NOIRLab, such as Rubin in-kind or SOAR or Las Cumbres, you would submit a proposal to the NOIRLab CSDC TAC, which means that if you need to use the entire network, you will probably need to submit the same proposal basically in 2 avenues, to Gemini and to NOIRLab. And so we're now working on implementation details and software requirements so this can be done relatively straightforwardly. Then we can keep track of the different pieces as they work through the system. And we hope to have this working for the 22B call for proposals, which is next March. So Gemini currently works within Aeon via a plugin for the TOM toolkit and some existing APIs we have. As you can see here, a little screenshot, the TOM plugin provides an interface for requesting Gemini observations manually. It also allows us to do automatic triggering based on all the features in the TOM, and you can see an example of that coming up. And this all is done via one API we have for observing database, which allows these parametric submissions, which works fine, but is rather limited in capability, and we'd like to improve that into the future. You can get more information about this, the documentation, and some example scripts here at this GitHub repo. Our archive also has APIs which allow the programmatic downloading of raw data, and you can get more information about that there at these links. So I'd like to show a little movie about how all of this is working at the moment. So here I've imported a ZTF target into the TOM, and I'm checking the visibility. And it looks like I can observe it. So I'm going to submit a Gemini observation. I select my TOO template. I'm going to give it a group title. I'm going to want the slit at the parallactic angle. So I need to enter a date and time where it's likely to be observed. Brightness, air mass constraint. I'm going to add a little note. And now it's going off and searching for guide stars, submitting the request, and there's the result in the TOM database. If I go over here to my OT, there, the observation has appeared with all the information. There's the guide star and the slit at the parallactic angle. But the real advantage of this is to be able to do things automatically. So I've set up an alert broker query, which I run it. Anything that matches the criteria programmed in, it will automatically submit the TOO request. So there it's gotten 2. I submitted a rapid TOO to Gemini South, which is there. And then if I switch my authentication so I can look at Gemini North, there's a standard trigger that got sent there without me having to do any extra button pushes. I just pressed run on the query. And then back here in the TOM, you've got the information in the database about the observations you can use to track their progress. But Gemini will support Aeon even better via the Gemini program platform and Gemma projects, which are underway. So this GPP is the core of a new observatory control system, which is a high-level software. The main goal of this is to make the whole process easier for everybody. So it's going to replace the phase 1 tool and the observing tool and all the other high-level tools eventually. It's a set of web applications on top of APIs with an underlying database, which will allow both Gemini North and South observations in the same program. Between the interfaces plus the APIs, it's going to promote a lot of automation. It provides the constraints we're going to need for the scheduler, and it just makes the code more maintainable and expandable for the future. And you can get more information about the links down here. And I will post this talk after this so you can get at all those links. So GPP is now under construction, and it has advanced a long way since the last time I updated you about this at the last Gemini Science Meeting. 3 years ago, I gave this sort of concept about having a phase 0 tool where you could enter your science requirements, your resolving power, the wavelength coverage you wanted, and the tool would give you the list of Gemini instruments and modes which met those requirements. And now, 2021, we actually have the first version of that working, as you can see here. Also in 2018, I gave this little sort of cartoon mock-up of showing that we want to move towards going on physical conditions on targets rather than the percentile bins that we'd be building around the ITCs. Now, this is actually in working. Here we have physical conditions being entered on target. And the IC integration is ongoing as we speak. Another advantage is because we're building this up from scratch. We're able to include lots of undo and redo features that people have been asking for years and years. So we anticipate community testing to start on this early next year. We hope to organize a testing group or advisory committee by the end of this year and do demonstrations with people at the January AAS. Thanks, I see the stars. And early testing is going to include, just using the system, filling in questionnaires, and we're going to do quantitative use testing to see it's actually faster than the current system. So let us know if you're interested in participating. And in late 2022, we plan to start early science in a phase we call XT. XT1 will use about 10 hours per telescope for GMOS imaging and long slit observations with this system to allow us to test the scheduler and using both telescopes sort of as a unit. As we implement more instruments and modes, we'll be doing XT2, what we'd like to do is convert existing programs into the new system, and we may give people a little bonus as a motivation to do this. And we expect full operations in around 2024. And finally, we're implementing real-time scheduling and data reduction as part of the GEMMA project. The scheduler is now in prototyping and design stage. And the idea is that it will update the plans in real time as weather changes, TOOs come in. It'll schedule both telescopes together. And here's a result of our prototype scheduler where it does that. And it provides much more capable APIs, especially for all this automation and TOO observing. Real-time data reduction is in the works as well. You saw the update from Kathleen yesterday on the Dragons pipeline, and there's the workshop this afternoon or later today. This is to do initially GMOS imaging and long slit. The quick look reduction for quality assessment is in use now, and science quality is coming for next year, along with the needed archive updates. So in summary, we're aiming to be the premier 8-meter class member of a follow-up network consisting of the brokers, the TOMs, dynamic scheduling, a range of telescope apertures, and real-time data reduction. We're constructing this new observing system, support follow-up, and make Gemini easier for everybody. And community involvement will be vital to make this really work for everybody. So please participate. Thank you very much.
Awesome. Thank you so much for that. Let's see. We don't have a question. We have a comment from Wesley that if you have identical observations and more than a couple of targets set up the way that you showed in the video, it's very easy to do. So someone is already giving you kudos for this. So that's always good to hear. Let's see. Thanks. So Meg wants to know that that Rubin operations are expected to start in April or June of 2024. Right. Is GPP kind of planned to start around the same time?
That's the goal, right? We're limited by, or the deadline is that we need to be operational enough to commission Scorpio. We will not be commissioning Scorpio with the current OT. So we're driven by that. And of course, the goal is to have all of these improvements for TOO ready by the time that the Rubin alert stream really starts up. So
fantastic. As someone who is on the Gemini side of the TOO OTs, it'll be nice to have things very automatic. Yes. Let's see. There are no other questions. So I do have sort of a procedural question, I guess. So it does look like it's quite easy to trigger on a target through the new setup. What happens if you have multiple teams, different teams, triggering on the same object through sort of the same pipeline? Is there a way to fairly distribute those, or is the data going to be put into sort of a central location?
Right. We will continue to follow the policy for competitive TOOs that we have now that came out of our experience with the Kilonova follow-up in 2017. So check the webpage, and I got a link to that in the workshop talk from yesterday on that too. It's basically, we've set down, the way we're going to make those decisions in terms of, queue programs over DD and a sort of first come, first serve. But if multiple groups trigger observations that use the same instrument and mode, like GMOS with the B600 grading, if we have like 3 teams wanting that same data, we reserve the right to share that data with everybody. But we don't want to get caught up with a lot of negotiation beforehand. We just want to get the data, and then we'll sort out who gets it later. In GPP, we'll probably try, in the scheduler, we'll try to codify all those policies. So we'll have to keep track of who comes in and put all that into algorithms, and so it'll be sorted out fairly.
Okay, wonderful. Great. And we have a question from Joel that is, will the Tom-generated observations receive the traditional phase 2 checks? Which seems like a good question.
At the moment, they do, because we have these template observations that you use to do the trigger, and those are all checked at phase 2. With GPP, the idea is that you could still use a template observation if you wanted to, if it's something special. But the idea is that you'll be able to create observations automatically with our new, it's like using best practices, the best sequences. You give us, I need this wavelength range, this resolution, and we'll just fill out the observation for you. It'll be all, using, again, best practices. It'll be executable. You won't need to have a person check it if you use the automation. And so you can just create observations from scratch and send them in without needing to be checked.
That sounds great. Awesome. Well, we are at the end of our time. There are a couple more questions there that after this you may want to have a look at, Brian, and see if you can answer them. But now we will move over to our last talk of the day. So if you can stop sharing, and then we will hand it over to Pat here, who is going to give us a talk about NOIRLab and Gemini in the 2020s. Let's see. So Pat McCarthy, who is our director at NSF NOIRLab here, will sort of finish out our last talk of the day, discussing the future.
Great. Thank you, Jennifer. Can you hear me?
Yes.
Aha, good. Now, let's see if you can see my slides.
And we can see your slides. Perfect.
All right, you're wrong. Well, thank you so much, Jennifer, and thank the organizers for giving me this opportunity to talk about the future. It's always my favorite topic. But first, we're going to take a little look backwards, because it's always good to know where you've come from before planning for the future. We'll ask ourselves, what worked, and take some lessons from the past. Then I'm going to talk about why I think the 2020s is the decade of the 8-meter class telescopes. We'll pivot a bit then and talk about the U.S. Decadal Survey for Astronomy and Astrophysics in the 2020s and what impact it might have when we see their report. And then just a little bit about setting the stage for what comes beyond the 2020s, and that might feed into the panel discussion that will follow. So let's first talk about the science landscape. I think this meeting has been quite interesting in showing the breadth of science that Gemini enables. We saw some great talks today just about the solar system from Meg. Really shows us about clues to formation and evolution and dynamics. Earlier in the week, we saw some fascinating talks about exoplanets, where we've really gone beyond detections, but now talking about atmospheric physics, about composition, about dynamics. It's really quite a burgeoning field. Lots of talks around interesting and extreme environments. Some good talks today about the extremes in Kilonova, detection of emerging neutron stars, that burgeoning field of multi-messenger astronomy that really probes some of the most unusual locations in the universe. And then much of what we've heard and been seeing from Gemini for years feeds into this our desire to understand the universe at large, the physics that drives it, in particular where galaxies come from and how they form and how they evolve. If you look by comparison then to the structure of the US Decadal Survey science panels, it's kind of interesting. So this is how the Decadal Survey has organized its thinking about scientific frontiers for the 2020s. You can see the topics actually map very well to what's gone on in this workshop and really what goes on within all of NOIRLab and Gemini, talking about these compact objects and their highly energetic phenomena, talking about the universe on the largest scales and the galaxies that fill it, and then locally looking at how stars and planets form, how exoplanets form and might host life, and then lastly coming back to our own solar system and asking what can it tell us about stars, about star formation, and ultimately about planets, and again, that search for life. So I think where we are now with our whole organization in Gemini is really very well aligned with the contemporary science, and particularly where we see the whole field of astrophysics moving in the next decade. And that's a great place to be. So let's look back a bit, because it's shocking to know how long it's been since the first 8-meter class telescopes went on the sky. It's been a bit over 20 years for Gemini, but it's coming up on 30 years for the first time, say, the first Keck telescope opened up the dome. So we might ask, what have we learned in these 2 to 3 decades of using 8-meter class telescopes? Well, we've learned a vast amount of science, a great deal about the universe that we didn't know. We've learned a lot that now we don't know that we thought we knew before. But we've also learned some lessons about observatories. And I think one of the key lessons is that continuous reinvestment is essential. It's so common in our field that we put a lot of effort and energy and resources into building an observatory, and then we starve it of instruments and we starve it of operational funds. And part of the keys to the success for Gemini has been continuous reinvestment in instruments and adaptive optics and other systems. That's what keeps the telescope forefront. That's what keeps it at the cutting edge. And that's done not by just allocating budget resources, but by building teams of scientists and engineers, in particular scientists at the universities or in our partner institutions who have an idea, have a passion for the science, understand what they want to accomplish, and work with skilled engineering teams to go from that vision to a fully integrated instrument on the telescope, working with the observatory staff to make sure that their vision can become a reality and that it can be useful for all of the users in our community. And I think we want to make sure that as we go forward to this decade, that we continue to support that investment in new technology and that team building and the partnering that's so essential to our success. One of the things we learned from the 8-meter era is that ground-based synergy is really powerful. And that was demonstrated early on with Keck and Hubble that came on the sky at about the same time. And together, the two of them were vastly more powerful than either would have been by itself. The fabulous imaging from Hubble, coupled with spectroscopy from Keck and others, really opened a whole new world in the distant universe. Since then, we've seen Gemini and others work the whole host of space-based assets, whether that's in the gamma rays and X-rays, the far infrared. There's a lot of great science that comes by combining different parts of the spectrum, different ranges of resolution, both spatial and spectral, and leveraging that strength of the ground and space. And I think we're going to see more of that coming up in this decade. A key message, and I think we've seen this a lot today, is that innovation never goes out of style. And that while we may have the same platform that's the telescope, we can renew it not just by building instruments, but by changing the approach to how we use it and how we support science. And some of the innovative techniques that Gemini has brought for the long programs, the fast turnaround, the director's discretionary time. I don't know how many talks I've seen this week that stress the flexibility of Gemini, its ability to respond in a way that's tailored to the particular science problem, has really maximized its impact. So we need to keep thinking, we need to be agile, and we need to keep innovating, because there's lots of new things we can do with these tools, despite the fact that they're getting fairly mature. We should also be a bit sober about how long it takes to develop technology. There's some interesting examples. The time between the first photograph taken and when photography really became a widespread, both popular and scientific application, really at its zenith, was well over a century. And it took about 25 years from the invention of the first CCD to completely drive photography more or less out of the marketplace. So innovation, while it can be agile and quick, technology often takes time to really sink in and reach its full maturity. And we see that in the construction of observatories. It was close to 50 years between the dedication of the Palomar 5-meter and that for the first 8 to 10-meter telescope, the Keck 10-meter. And it's going to be 35 to 40 years between first light on the first 8 meters and first light on the ELTs. It just takes a long time to build these big systems and for the technology to mature to allow that next big step. I think that's important to keep in mind when we look at some technology we're wrestling with today. Adaptive optics is still a relatively new technology. The concept might be older than most of us on this call, but the technology itself has only been around for a few decades, and we're still learning how to use it and how to build it and how to optimize it. So I view the future for adaptive optics is bright because there's a lot of room for innovation still. It's still a relatively new technology. So my takeaways from looking back is that we need to invest early. We need to continue to invest. We need to build and maintain and sustain our partnerships. And we have to be patient, but just keep pushing because it takes persistence to make these things really pay off. So if we look forward, I'm convinced that the 2020s is the era of the 8-meter telescopes, both on the ground and in space. Webb is, it's an 8-meter class telescope. It will have diffraction limited imaging that's comparable to the 8 meters, working out at longer wavelengths. Its sensitivity in the thermal infrared will be really unrivaled by anything. It's going to be spectacular. And I think it's going to rejuvenate this ground space synergy that we saw with Hubble and we've seen in the gamma rays and X-rays. And I think we've already seen at this meeting, people who showed exciting Gemini science and said, oh, this great result from Gemini helped me get time on Webb on cycle 1. And I think in a little while, we'll see that go the other way. People have their exciting Webb data, and they're going to want to come to Gemini and other telescopes and get that spectroscopy, the AO imaging, the other wavelengths. That synergy, I think, is poised for a real rebirth when Webb launches and we continue to build out our adaptive optics capabilities on the ground. And I'm already seeing Joanne's stars picking up. So the Rubin Observatory is coming soon. So we'll have lots and lots of imaging, but remember, spectroscopy is what drives astrophysics. And the combination of Rubin and faint spectroscopy is going to open up whole new windows, not just in the time domain, but in the static sky as well. And this is just illustrated in this nice little diagram showing the imaging depth of Rubin and some infrared space telescopes, Euclid and Roman, that are coming, and how Gemini can push well into that imaging domain with a spectroscopy, followed by Webb, and then eventually the ELTs. It'll be able to get spectra of essentially anything in the Rubin static sky and most anything in the Roman survey images as well. As I said, AO is still a young technology, but it is the future. The 4-meter telescopes really delivered on their full promise once they cleaned up their image quality and got digital detectors in to replace photographic plates. And now the 8 meters with AO, they're reaching their theoretical limit. And so they're performing almost as well as they can. There's a little more room to push, and that's what's going to make this so powerful. And they are the key. AO and digital detectors, low noise devices, that's what will drive the performance of the extremely large telescopes. And Gemini and others, they're the pathfinders for that. And so it's important that we keep reinvesting and finding the right technical paths forward. So the US Decadal Survey is coming to a conclusion. That's the body that will set our scientific priorities for the decade and our priorities for investment in the federal agencies. I don't know what they're going to predict or prioritize for the big projects. I think it's pretty safe that they're going to advise us to invest in data archives, to invest in high-value data products, to include more people into our communities, those who've not been able to participate, and to engage more closely and with more respect the local and indigenous people around our observatories, and to reduce our carbon footprint and be good as citizens and make our observatories green. And all of these things are in our vision for the future, and we're committed to moving forward on all of these initiatives. In that vein, the themes for the NOIRLab in the 2020s are to become the leading resource in time domain astronomy. We heard about that from Monica and Brian. To push high precision astronomy, whether that's adaptive optics, precision radio velocity, spectroscopy, lead the world in survey astronomy, and of course, engage the community and really be an agent for positive change in our field. And Gemini touches all of these boxes. And then when we bring the entire lab together with Gemini, Rubin, the mid-scale observatories, this is our theme, our vision for the 2020s. We look out then, how are we going to build this from a science perspective? One of our themes is we want to image the sky in depth, in color, and in motion. And we'll do that with our wide field imagers and the precision cameras. We'll do that with ground space synergy, and we'll do that in the time domain, as we saw from Brian, by building these intelligent networks that connect Rubin to Gemini, to SOAR, to suites of small telescopes, and open up that new domain. So lastly, if we just step back and look to the long-term future, what do we see coming in the future decades? Well, first and foremost, we want to continue to invest in Gemini, and not just in its operations, but in development of new technology, because that's going to push science for some time. We've got some interesting experiments going on in dark energy. We've got the Rubin Observatory coming in just a few years. We'll have to build something that uses those facilities afterwards. We may have, one or more, hopefully two 30-meter class telescopes built with US involvement and operating in the 2030s and beyond. And at some point, we need to think about what's the next big thing. In order to do that, we need to start planning. We need to invest in technology. We need to build the community and make those plans for the next generation of young, clever people who will do interesting excitement. And that, of course, is all driven around this decadal process that's coming to a conclusion now. But once that's over, it's time to catch our breath and start thinking about the next decade. So it's been a bit of a whirlwind tour. I think we've learned a lot, but the future is very bright. And I think the next decade is going to be an exciting time for all of us, particularly for those of us in the NOIRLab community and Gemini in particular. So thank you for giving me the opportunity to just share my thoughts on how I see the future. And back to you, Jennifer.
Wonderful. Thanks so much, Pat. Let's see. There are no questions yet, so get those questions in, everyone. In the meantime, my question for you is there a specific astronomical question that you hope is or excited about maybe being answered with the help of Gemini over the next decade or so?
The big question that I hope that I'm around long enough to see the answer, but I'm convinced that some of you will be, is there compelling evidence for life elsewhere in the universe? And I think we will actually have the answer to that in the next maybe decade, maybe more. So I'd like to be around to see that happen. I think some of the results we've seen about atmospheric spectroscopy this week point the way. It maybe that's too hard of a question for the 8 meters, but finding the right systems, developing the right techniques, setting the stage, that's a huge contribution. We would never get there if we don't do that with the techniques and the tools that we have now. And I'm very optimistic on what I've seen in the past few years. That with precision spectrographs in the visible and the infrared, we have a good chance of seeing the atmospheric signs of biology in exoplanets.
Fantastic. Yes, I've only been here for 6 months, but seeing the wonderful things we can do when observing, it's fantastic. Let's see, there are any other questions, anyone? Everyone seems to have, maybe everyone's taking their break right now. So then another question, since you are the NSF NOIRLab director, how do you see the non-Gemini telescopes contributing together with Gemini in the future? Or what sort of unique capabilities are they adding to the Gemini telescopes that maybe weren't working before NOIRLab?
Yeah, well, we saw a bit of that in the discussion from Brian around the time domain, but I think there's a lot going on in this what we might call the static sky that is powerful but less appreciated. So the very large sky surveys, like the Dark Energy Survey, what will come out of Rubin, the spectroscopic survey coming out of DESI, they find interesting rare objects. So whether that be quasars beyond redshift 6 or something that are probes of the early intergalactic medium. Those big surveys are the hunting ground for the really interesting systems that then you can go back and study with Gemini with its narrow field, high quality, high contrast imaging AO. Gemini is not so much an instrument for surveying large patches of the sky, but when you know where you want to look, that's where it's powerful. And now by having all of that sort of under one roof, I think we can leverage that more effectively, not just in the time domain, but also all kinds of different areas of parameter space and color space and color magnitude space to find those interesting rare objects that often tell you an awful lot about what's going on that you can't learn from huge samples of sort of run-of-the-mill objects.
Wonderful. Let's see. Oh, and we do have some questions coming in. One is NOIRLab seeking collaboration with other observatories specifically to help achieve the decadal survey goals?
Indeed. And when we know what those goals are, that will make it easier to. But I think some of the things that are more structural and social to the field about bringing other people in, building data archives that are robust and useful to a large segment of people. Those are conversations we're already having now. I think there's a general sense building within the field that we need to get everything out of every bit of data that we can, that we need to treat our mountaintops in a way that minimizes our footprint and shares them with local people, that we need to bring more people into the field. And so those are things that are happening across the field. And we're having good conversations with other observatories around those very issues. But we're also talking to people who are interested in massive spectroscopic survey telescopes. We're talking to the ELT project. So when we see the direction on the big projects, we've already built a lot of that groundwork to move in those directions of working in partnership with those groups. We just need to know what the direction is, and hopefully we'll know pretty soon.
Wonderful. So then another question about instruments from Zach is, for both Gemini and beyond to other NOIRLab telescopes, is it more likely that new instruments will be focused increasingly on specific science questions, or is there going to be space for new general use instruments to be developed?
Oh, I think there's space, but particularly in Gemini, I think Jennifer Lotz works with her the GSTAC, the Gemini Science and Technology Advisory Committee, to get their guidance. She works with the Gemini Users Committee to gauge their interests. So we're very much tuned into what does the community want, what do the technical experts think is feasible, and that will drive which way this goes. Whether it's things that are very specific, and we've seen some really powerful examples, say with Maroon X, the things that are very broad like GMOS and maybe, you know, daughter of GMOS, whatever is coming, I'm hoping that will be a general purpose instrument. So I think there'll be a good balance, but it's driven by the community, and the Gemini leadership is very responsive to that input. And I'm sure that they're going to think carefully about what comes next after the many exciting things in the pipeline you've already heard about this week.
Great. And then one final question before we move over to the panel. So Meg wants to know that, so Gemini has been groundbreaking in international scale partnerships in large observing facilities. So how is NOIRLab utilizing that expertise and experience from Gemini as Rubin Observatory and the US involved 30-meter telescope progress?
I think we've seen examples this week and over many years of how Gemini's used its international partnerships to leverage interesting and important contributions. Ones that are just coming are IGRINS and IGRINS 2. Many of the instruments that are powerful now have come out of Canada. Some have come out of Australia in partnership. So I think the partnership has been very vital and engaged in building instruments and setting directions. We're always looking for new ideas and new people to bring into the fold. And on the ELTs, of course, when you look at the combined global community within the Giant Magellan Telescope and the TMT, they cover pretty much every country that's interested or really a player in astronomy that's not in Europe. And so when thinking about to find new partners, say in the ELT sphere, I looked around the entire globe and was thinking, surely there must be more countries, because everyone who's a player in astronomy is in one of those groups or another, with a few exceptions. And we should be working on those few and to try to bring them into the fold. Like thinking like, you know, Taiwan, for an example, is a great astronomy group, technically capable. It would be nice if we could find a way to get them into some of these big projects. So, you know, astronomy has made the world much, much smaller. Those international partnerships are vital to all of us, and we need to just keep building on them and nurturing them. But we're pretty well connected. And Rubin, while it's being built in the US, the technical and scientific network is very broad, and it's very well connected all across Europe, parts of Asia as well, even parts of South America and Latin America. So it's a much more diverse project than you might guess just by looking at the hardware itself.
Great. All right. Thanks so much, Pat. And actually, you're going to stay on. I'm going to hand it over to Janice, and we will start the panel discussion then.
Thanks, Jen. And thanks to all the speakers in this session. All the speakers over the last 3 days, they've been excellent talks and have paved the way, in fact, for a lot of this discussion, in particular, our session on TDA and Pat's talk just now. So
Shall we start on time?
Please go ahead.
Right. I suspect people will be trickling in as we start. Well, first, welcome. Thank you for showing up at the end of this week of talks. So we have an hour. There's a lot I'd like to cover, so there will probably be things I will be forced to skip. But one thing that I want to make sure you realize is all the material is online. The documentation, it's on this Read the Doc, the workshop. Everything is there, including the exercises, how to download the data you need, and also all the solutions are there too. So as I go through it, I will either be too fast or too slow. I don't know. I'm not with you in the room to feel the room and know. So I apologize in advance for whichever faux pas I make. But you will have the opportunity, and I strongly encourage you to go back to the workshop material on Read the Docs and go through it again at your own pace when you have the time. So the way the workshop is structured is I will, in the interest of time, I will define a few terms and do a few demos in the first part. And in the second part, you will have the chance to do some exercises. If you don't have Dragons working right now, don't worry. Most of the exercises is just about figuring out which command to write. So you don't even need to run it. And in fact, we won't run most of the commands we will figure out. So this workshop is not about how to reduce data, because we would need a whole day for that. It's about how to customize dragons, how to tame your dragons. So let's get started. And here we go. So what is Dragons? It is a pipeline, but it's not a completely hands-off pipeline. It can be automated, it can be customized, it can be run interactively, it can be scripted. It's really at the discretion of the users. But we do try to optimize all the algorithms and the default parameters such that for most of the programs, if it runs completely hands-off, it should give a pretty good result. Of course, programs are different, sky conditions are different, so that's why we also provide the ability to customize and tweak and optimize the reduction to really get the most out of your data. Currently, it is focused on Gemini data, but we do have some hooks to support other type of data. It's not super clean. I hope that one day we get to that. So yeah, we thought early on about how we could hook other data, but for now, just Gemini data. We have our hands full. We really cannot support other type of data fully. The components that we will look into today, I'm not going into the details of implementation, how they work together, but we will talk about astrodata tags and descriptors later. That's how those you can use to create your file list, and the recipe system, basically what reduce, a command reduce that we will use today. What it does, it's the infrastructure, the automation, that's what is the core. This is how it knows how to recognize the data and which recipes and primitives to use. It's through astrodata. We have the calibration manager, which allows the reduce to automatically retrieve the most adequate process calibration. So you don't have to put it on the command line or in your script. And then as part of Dragons, there's a whole set of libraries of recipes and primitives for the Gemini data. Currently, the public version has support for the Gemini imagers. What it is not, and here I think it might be my most important slide of this workshop, it is not an analysis package. So if you want to measure redshift equivalent with, do photometry, that's not it. Dragons will reduce the data up to the point where you can do these measurements, with whichever tool you prefer, but it will not offer analysis tools. It is also not a replacement for RF. RF is huge. You cannot expect us to replace that. It is, if you want to call it a replacement, it's a replacement for the Gemini RF part, which Gemini RF also is not an analysis package, it's a data reduction package. And before we go to the workshop material, and by the way, this is essentially the first two section of the workshop. A typical usage, just to get people oriented, and thank you everyone for filling in the poll. It confirmed that most of you never used Dragons. So just to get you oriented, and I will do a demo of that later. A typical usage is you create your list of input data, and we have tools to make that painless. You initialize your calibration database. The database is just a small SQLite database. It takes no room. It's very simple. It's just a file. And then you reduce your calibration, make the calibration database aware of those newly reduced calibrations. And then you reduce your science. The calibrations will be picked up automatically. And the few lines, 6 lines there, well, if you had NIRI data, very simple program, that's pretty much all you would have to type. So it can be that simple. So with that, I will switch to my desktop. Give me a second here. Oops, not leave meeting. Whoa. Okay, share. So can somebody confirm that you're seeing DS9, the workshop material?
Yep, you're good. This is the same one.
Thank you. Thank you. Okay, so let's start defining some things. Dragons uses, and by the way, I'm sorry, I'm looking at my desktop, so I'll try to talk to you and see what I'm doing. Dragons uses a set of recipes which calls primitives. So recipes is, as you can think, it's a set of instructions that will get from raw data to your final product. The primitives are the steps in between. So if you look at the workshop material here, this is a recipe. Reduce, not very imaginative, but that's the name of that specific recipe. For those who know Python, it's essentially just a Python function. And here, prepare, add DQ, ADU to electrons, flat correct, dark correct, those are the primitives. So the primitives will affect your data, will do something to your data. And as you can see, we really try hard to name our primitives in a way that will let you know more or less what is happening. So we try to keep the scientific meaning of the step. So essentially, when you look at the recipe, you should be able to read it and have an idea of what is going on. Of course, you don't have the details of the algorithm underneath, but you have some indication, like this will dark correct, flat correct, do the sky correction, and align and stack the data. So that gives you an idea. Now, this is all good, but the first step is how do you get to see those recipes? So what I'm going to demo now is how to inspect which recipes are available, what they look like. And then, as I mentioned, you can also customize things. Well, you will customize the inputs to the primitive. So I will show you how you can see for a given primitive which input parameters you can adjust. And we will I demo it now, but we will use those principles later in the exercises. So I'll just skip to a good demo step. So I want to know about a recipe. It's called show recipes. So it shouldn't be too hard to remember. And now one thing I always forget to do, I need to get into the right directory where my data is. So if you downloaded the data package, this is all data that you downloaded. So that's where I am. And I'll just clear this. Here we go. Okay. All right. So I want to know, I have this file, and I know that this happens to be a Gemini Science image. And I want to know, what the recipe looks like, what's going to be run on this thing. So show recipes, name of the file, and it will show you the recipe that is the default recipe that is associated with that file, with a NIRI image. So the recipe tags, that's for a NIRI image. And this is all the primitives that will be run sequentially on it. Things that I want to point out now, and I will point them out later. Yeah, I agree, format is not spectacular, but the information that you want to be aware of is the name, the input recipe, the name of the recipe. So you know if you decide to edit the recipe, and we will do that later, that's the function you need to find. And the recipe location is another useful information. If you want to make modification to that recipe, you copy it over, and then you can make modification. And again, we will do that later. So this is nice. It shows me what is the default recipe. The thing is, the recipes are grouped in recipe libraries. So the libraries, their characteristic is they will work for a certain type of data. So if I have several recipes that I want associated with NIRI image, NIRI Science image, then I have a library with all those functions in there. There's always one for each recipe library. There's always one that is default. But there are others. Let's say you want to see what the others look like. Well, show recipes, the name of the file, and show me all of them. Wow, why is it taking so long? And here we go. Here are the names. It's Python syntax, but these are the recipes that are available. One thing I want to note, not because we're going to use it, but just to avoid confusion, you have two reduces. You have these things. There are actually different recipes. One is for SQ. SQ in Dragon's World is for science quality. QA is for quality assessment. So when you do show recipes -all, ignore the QA recipes. They are used internally at night to help our servers make the decision. So we do some automatic reduction at night, very crude, but just to help to figure out what the sky conditions are. So that's what those recipes are. You never want to run them. Just focus on the SQ recipe. Those are the ones you're interested in. And just a heads up, in the next release, you're going to start seeing QL recipes. Quick look. For GMOS long slit, those will be the only one available, just for a quick look. Okay, so let's say I'm interested in this make sky flat recipe. I want to see what it looks like. So again, what I will do is show recipes, name of that file, and a flag that you will see here and you will see again with reduce is -R for recipe. So that's the mnemonic here. I want to see the make sky flat recipe. And I apologize, I have no idea why it's so slow. So here we go. I confirm that the recipe I'm looking at is make sky flat. It's in the same recipe library as the other one. It's just, it's not the default one. And here's what it does. And if you're curious, and if you work in NIRI in the terminal bands, L, M, and M bands, you want your flat to be created from your science image when you have just 4-point sources. And you would use this specific recipe. So that's how you inspect the recipes. The next thing to inspect are the input parameters. So that's very nice. Let's say I have, let's say normalized flat. I would really like to, well, this is, yeah. I would really like to know what I can fiddle with. For some reason, normalization is not working. I want to change to something. What can I change? So that is with show pars. Pars is a short version of parameters. And here in the workshop the document, I show you what the syntax is. And I do want to talk about this a little bit. So show pars, the name of the file, and the name of the primitive. Now, one common question is, well, I want to see what the input parameters for normalized flat before dark rec are. Why do I need to provide the name of a file? That is because just like for the recipes, the primitives are also associated with specific type of data. So the NIRI flat input parameters are likely different. Well, even if the parameters are the same, the defaults are likely different than from GMOS flat. And still the primitive will have exactly the same name. So that's why it's very important that you do add the name of the file that you're going to work on. So let's see how it works. And in fact, this one, I just want to copy paste because typing can be a bit annoying. So here, show pars, the same NIRI science image. I want to see what is available for dark correct. This one is a very simple one. I'll show you another one. And here we go. This one is very easy. Essentially, what you want to do is either to turn it on or off. Maybe a more interesting one would be, let's see, sky correct. This one you can really fiddle with. So it doesn't even fit on my. So reset sky, scale the sky, offset, save the sky. The operation you do to combine the sky or calculate the statistics. So you can really, depending on the data that you have, you might want to fiddle with that or experiment with these things. So with show pars, this is how you get to see what you can change. And I will show you later on the reduce command line how you can change that. And since I mentioned the reduce command line, so today I'm just working from the command line, but just know that if you're a Python coder and you like the script, everything can also be done through the API. It's completely out of scope of this workshop. So moving on. Now I will do a little demo because most of you have not used Dragons, you haven't seen it in action. This is a very, very short, a much shorter version than the actual NIRI tutorial. So if you want to see the full reduction with a bit more bells and whistles. We have the NIRI tutorial that goes through those steps and a few more. So it's also on the Dragons Read the Doc space. So the steps, as I mentioned, you set up the calibration manager, you create your file list, then you basically start reducing. So it's really straightforward. And here I am in my reduction directory. Let me just clear it up completely, just to make sure now it's completely clean. I won't have surprises. And I'm going to reduce NIRI data with the calibrations from raw to the final product. And yes, it fits in just in a few minutes that I have here. We will, the first exercise is about the local calibration manager. This is the bit that actually has created some confusion. So I will try to demystify it. It's really not complicated, but maybe by doing it yourself and switching between calibration managers, it will become clear in your mind. So just so you know, it relies on a configuration file. Now, often configuration files are scary. This one is the simplest configuration file in the history of configuration files. You have calib, standalone, true. Those two lines you just leave there. You never have to change that. For those who are curious, yes, it can be false, but only at Gemini. It's an internal thing. The field that you care about is database dir. So it's just a directory on your disk. It can be anywhere on your disk. It doesn't need to be where you're reducing the data. It really can be anywhere on your disk. So that's the configuration where you want the little file to be created. And let me just go ahead and by the way, let me just show you what my calibration file looks like, because that will give you an idea of what the exercise will be about. So this is what it looks like. Currently I'm set up just like ready for the workshop. But for each project I work on, a different tutorial or helping a user, different help desk, I create a different calibration manager. I don't know how many calibration manager I have on my disk, but they're all controlled through this database dir field. And in my file, I have a lot of them, but only one is activated. So all the other ones are commented out. Okay, so that's the key to remember. Which one you're going to use is the one that is commented out. So let's just get out of there. And right now I have nothing. I do CalDB init, and it creates this little database. And here it is. If I look into that database, CalDB list, it will say, well, I'm empty. I have nothing. I haven't started. Makes sense. If you have your configuration files set up and you have downloaded the Google Drive, the extra Google Drive files, if you do CalDB list, it should have two files, the flat and the dark. So let's start a reduction. I'm ready to go. Step one, create my list. And to create the list, it's the tool data select. At the very end, I don't know if we'll have time, but at the very end, there's a series of examples and an exercise that I think will be a take-home exercise with data select. You can really go and pick exactly the data you want to create the file list. So in this case, I want the darks with an exposure time of 20 seconds. Here I'm using tags. Here I'm using descriptors. So I want to define those two. The tags, or the astrodata tags, they're basically the nature of the file. So you will have NIRI flat or NIRI dark, GMOS image, things like it's really the nature of the data. Things like exposure, filter name, object, it's more like the flavor of the data. So that's what conceptually distinguishes between the tags and the descriptors. So you use the tags here, they're always in capital letters, and the descriptors in the expression. So, and the syntax is Python syntax. So let me go ahead and quickly create the list of dark, the list of flat, the list for the standard star, and the list for my target. And it will go in the directory where I have all the data and create all of the lists that I need. Okay. And here I have my list. And one thing I want to point out, let's go to, I check the flat. You could, it's Unix, so you could redirect to a file. I strongly suggest you use the -O, basically to create the output file, because it will add the criteria that you use to create that list. And I found when it's time to debug, it's somewhat useful at times to figure out how you created that list. Okay, so now I'm going to reduce the darks. Reduce, the little @ symbol is it just to identify that it's a list that it needs to open. And here we go, I reduce the darks. And I don't need to specify anything else. It will open one, say, oh, this is a NIRI dark. Let me try to find the recipe for NIRI darks. Let me try to find the primitives for NIRI dark. Puts it all together, reduce the dark. I have my dark. It's this one here. So now I can add it to my calibration manager. And a note, just in case I forget to mention it later, it does not add the file to the calibration, to the database. It adds information about the file. So if you delete that file from here, it will still be, the information will still be in the database, but then when it Reduce tries to retrieve it, we'll say, it's supposed to be there, it's gone. So when you add the information about the file, not the file itself. All right, and this, the completeness, I do my CalDB list. Here I have this file in this location. Now I'm going to reduce the flats. The flats for this type of data, it's a series of lamp on, lamp off. I send them all in, and the algorithm, the primitive, will figure out, oh, these are the lamp on, these are the lamp off, fix them the right way, and off it goes, and will give me my flat, my NIRI flat. I have my NIRI flat. For those of you who've used Gemini IRAF to do that same thing, you would have spent 2 hours already by now. So, CalDB, I add my flat. Now I'm going to reduce my standard star. And here's our first introduction to how we can customize the input parameters. So for the NIRI standard stars, the darks are not taken. So if I try to reduce the dark, it will try to, and it's in the recipe, dark correction is in the recipe, and then it will ask, well, do I have a dark? No, sorry, and it will just stop. If a calibration is missing, it will not continue. So, but this time I don't have a dark. The star is so bright, it's not going to make a difference, and besides we do the sky subtraction. So in this case, we say, well, the dark correct primitive, the do dark input parameter, set it to false, and that will stop the dark correction. It will just skip the dark correction. It will still look for it, but it just won't do it. So, okay, I'm happy, that's fine. So the standard star, and I'll show the image later actually with my next the demo. It's basically, actually, it's still right here. It looks like this, and it's a dither on target. So the usual 5-position dither, I think. I don't need to specify anything. The algorithm is smart enough to recognize that it is a dither on target. And for the first frame, it's going to use the other ones to create the sky, then moves to the other one, will use the other one. As long as the time and they're shifted, it will figure out which other images it can use to create the sky frame. And here we go. I have my stack, my reduce. It's flat fielded, dark corrected, aligned stack. A sky subtracted, obviously. All right. Now I'm going to reduce my target. It looks like this. So it's an extended source. When you deal with extended source, you have to do an offset to sky. So in this list, and target that list, what I have is all my on-target observation, all my offset to sky observation all together. And again, the algorithm is smart enough, it will recognize the pattern and use only the offset to sky observation to create a sky. Now, another customization, this is a special case. My target really filled the field of view. So normally to fit the sky, the sky background with this background in your target frame. Well, this won't work very well because I have no sky in my target. It's just, it's filled with the galaxy signals. So I want to turn off the scaling. The sky were observed soon enough, it should be a good representation. So in this case, again, the primitive sky correct, scale the sky, not turn it off, false. And here we go. Now I want to point out that it will be dark corrected and flat field corrected. I did not have to say what to use. The calibration association is being done automatically. So the system goes, okay, I'm supposed to have a flat here. Calibration manager, do you have a flat for this data? And it will do the association. The association rules are the same as the one used in the archive, literally the same code. And it will look at, yeah, I have this one, here you go. And it does it. Now, it is possible to override this. And there's a section we're going to skip, but the information is there in the workshop material, how you can override the calibration selection. So here it is, looking at the sources, trying to figure out the solution to align my frames, and I have my stack. And we have gone from raw to reduce in a few minutes. And this is, if you're curious, this is what it looks like in here. And if you zoom in, the alignment, the automatic alignment is actually really, really good in this one. So that's what Dragon is. Now you produce stuff you might want. I said it's not an analysis package, but we do provide a tool to actually display the image because otherwise it would be a bit annoying. So we use reduce, and there's a primitive called display that we can call that will display to the S9. For something like NIRI, it's just one image, so it's fairly straightforward. But for GMOS raw data, when you have various amps and different extension and not necessarily in the right order, display knows how to piece them up together and display a nice image that we can inspect. So especially for GMOS, this is particularly useful. So let's just do reduce -R and display, and it will display the stack. And here, one thing that it does is it will label saturated pixels. So sometimes that could be useful. And the other one that I want to introduce you is inspect, which also display the data, but it will display, for example, a list. So one thing that I recommend, I always do myself, and I recommend that you do, is before you start your reduction, you create your list of raw data and you inspect them all. Now typing reduce R display for each one of them would be quite painful. So there's inspect instead, which will loop through the data in your list with a pause of, the default is 2 seconds. You can adjust it to whatever you want. And let's do this. Let's see it in action. And here you don't want to do necessarily measurements, but I really like to look at my data to catch anything that might be a bit odd. It's rare that it happens, but it does happen. So, and I'm a bit paranoid, so I always inspect my my raw data. Okay. Now get ready, it's your turn. Before we get too tired, we're going to look at the local calibration manager. That's if it's essentially that's the only topic where if you want to fully participate, you need to have a working Dragons environment. But the other ones, it's not necessary. You'll be able to follow even if you don't have a working Dragons environment. So if you have installed Dragons and you're set up correctly, you should already have a file in .gemini.dr, the file rsysconfig, that looks something like this. And if you want to check that it's configured properly, caldb config will tell you how it is being configured right now. So that's the file it's using. This is the directory that is specified. And this is basically the file with the directory that is going to be used. So if you've downloaded the Google Drive data, your playground directory should look like this. There's a cal manager, sorry, EB, and that's the one I just created in my case. And if I do the caldb list, there are two files, the flat that I just created and the dark that I just created. So assuming that you have this set up and remembering what I introduced earlier that I will remind you about is if you want to switch to another calibration database, all you have to do is go to the configuration file and create a new database dir field and uncomment it, comment the other one. So that's how you switch. Just activate the one you want to use. And to create one, when it's not being created, you do caldb init. Caldb init, you do that just once. I realized as I was preparing this that it should really be called caldb create, because that's just what it does. To activate it, it's really just a configuration file. So if you want to activate it, configuration file. If you want to create it, caldb init. So your first exercise is, so I have a caldb, a calibration manager in this playground directory. I want you to create one in another directory. Let's just say just above that, just the directory above that. It really doesn't matter where you decide to create it. So I want you to go to the calibration, to the configuration file, create a new database there, activate it, caldb init, and then do a caldb list to show that it's completely empty. So I'm going to give you a minute to try it. I'm not going to actually time a minute, and don't worry, give it a shot. I'll show you exactly how to do it. So, your turn. I can tell you as a presenter, it's very odd waiting for people to do something when the people are not present. If you want to follow along with calibration manager, the configuration file, I comment out the one that was activated. I activate the new one. One thing that I recommend you, well, I do all the time, I recommend you play with it as well, is caldb config. If you have, if you go from project to project, make sure with caldb config that you're pointing to the right calibration manager. You might get some surprises if you start using the wrong calibration manager. And here it confirms that now I'm using this calibration manager, and it also tells me, wow, it doesn't exist though. So do initialize it. So if I just go, it's not there. Oops. Now it is there. And I can confirm that it is completely empty. Right. Easy peasy. Now just an overview of the usage. There's another exercise. The usage, I've introduced CalDB config. Just use it a lot just to make sure you're looking at the right database. CalDB list, it's also useful. We've used CalDB add. And again, reiterate, it doesn't add the file, it adds information about the file. And CalDB remove, if you want to remove knowledge of that file from the database. Again, it will not affect the file on this. The file on this will stay there. It's just going to be removed from the database. So the other exercise is we have a new calibration database. I want you in the playground, you have a flat here and a dark. Just add the flat to this new calibration database, then confirm that it is there with the CalDB list, and then go back to the configuration file and reactivate the one in playground and check that now you see two files in that database. So once you've experienced how to switch the calibration database like that, hopefully you'll feel more comfortable working with them. So I'll give you a few seconds to play with that. So to add the flat is CalDB add. And I confirm with CalDB list that now I do have one entry for my flat. Now I'm going to switch back to playground by editing my configuration file. Activate playground, deactivate the imaging tutorial. I don't need to do an init now because it already exists. I can just do a CalDB list. And then I'm back in my original calibration database with the flat and the dark. So yeah, before we leave the topic of the calibration database, it could work if you decided to have just one gigantic database. Could work. I don't think would be a performance issue. I think scientifically it might be safer to have different calibration database for each project you work on. That is certainly my preference. All right, let's talk about reduce. If you want to see all the flags that reduce can accept, just do the standard -H or --help, and you will see the long list of things. We're just going to cover a few of them. The first one I want to talk about, it seems trivial to talk about it, but it's linked to a question that we get from time to time. When you run reduce, you cannot set the name of the output file. And the reason is because you don't really know how many files you're going to have. It really depends on the recipe that gets selected. It might produce 50 files or it might produce one file. when it comes to the implementation, it's a bit difficult to figure out a solid way, robust way to deal with that. So for the time being, what you can change is the suffix of the output, because you said that suffix, whether there's one file or 50, it will apply without name collision. So that's why only suffix is, changing the suffix is allowed. And it's very simple, dash suffix equal the suffix you want to use. By the way, the equal is optional, so you might see me use it or not. So now, more interestingly, and we've seen examples of that, is how to customize the primitives, the inputs to the primitive. As a reminder, if you want to see what you can change, you can do a show parse, and here let's show parse the normalized flat. And here because remember, you need to provide a file name. Well, normalized flat, usually I'm using a flat for that. So that file happens to be a flat. How did I know it was a flat? Well, I can check my flat list, and I can pick any one of them in my show parse. I just happen to pick the first one. So this going back to the show parse output. So for normalized flat, I have the name of the parameters that can be changed. In this case, well, you have the default value. In this case, this one accepts a set of different values. So that's a key. So sometimes it's a range. It will tell you what it accepts. And finally, as a reminder, it's reduce, name of a file or a list of file, -p, p for parameters, the name of the primitive, column, the name of the parameter, and equals the value, the new value that you want to use. So an exercise for you. I've already showed you how to do, well, it's like right up here, how to see the set of parameters that you can change. Now I want you to come up with the reduce command that will change the scaling to use mean instead of median. So just since you didn't run the demo, just a reminder, when we reduced the flats, it was, oh, is that 15 minutes, Jamaica?
Yes, it is.
It is? Okay, okay. So reduce flat, that's what we use. What do we need to add here in order to change the scaling on the normalized flat primitive to mean? Give you a few seconds. Think about it. All right. -p, parameter. I'm working on normalized flat column. And if I look here, statistics for scaling, parameter is named scale. So scale equals, and to do the mean, it appears it's just mean. And then I would hit enter and run it. So that's how I would customize it. If you have several customizations like that to do, you just keep adding strings like that for each one of the primitives and parameters you want to change. You don't need to repeat the -p. As long as they're all after the -p, it's good. Okay, running a non-default recipe. So let's go here. Well, as I mentioned, to see what non-default recipes are, you do the --all and show recipes. So let's say I want to run the make sky flat recipe. Well, we've already seen how it works, except we used it on the primitive. And it's basically reduce my list of files, -r, R is for recipe, although it works on primitives as well. So, but think recipe. And the name of the recipe. So now what I want you to do, we want to run make sky flat here. Actually, I think that's, yeah, make sky flat. on using the target image. So in the demo, we use reduce target.list. What do we need to add to run the make sky flat recipe instead of the default recipe? A few seconds here. Right? /r make sky flat. And if you're experimenting, I introduced a suffix ahead before. You like suffix test sky flat, or this is my sky flat instead. So it's the suffix can be useful when you start experimenting. For example, you just add it to the call. I mentioned earlier that you can override the calibration association. This is how you do it in section 7.4. It explains how you do it. We do not have time to go through that. And it's actually fairly rare that you have to do it, but we've had a few cases when it was required. Just know that it is possible. You can do it. Now, I do want to take some time to show you how to modify a recipe. And the most common case that I've seen so far was related to people who wanted to see the intermediate output. Because as you've seen when I reduce the data, I start from raw and I end up with the final product, which is great when everything works fantastic. But there's some cases where you might want to say, okay, but what does it look like after the flat correction? What does it look like after the sky correction? So in that case, that's a classic case of you wanting to modify the recipe, and that's entirely possible. So first thing you need to know is, where is that recipe? What is the recipe and where's that recipe? And that goes back to what I showed you earlier. The show recipe name of the file. You will have the name of the recipe. That's the function def reduce name of the recipe, and the recipe location. You might, just a note, you might see that some cases, I cannot really reproduce it all the time. Sometimes you get the .pyc. Well, just copy the file is the .py without the C. So I kept it in there because I think it happens sometimes, and it's information that might trip some people who are not familiar with Python. So I'm gonna do, because I think I'm in slightly different environments, I'm gonna show the recipe. That's how you would get the file, the recipe library. So recipe, you have information, this is where it is. That's the file. So I'm just going to copy this in my current directory. I always like to rename the file. It's work. I don't think it's necessary, but I just always rename it. So I know this is the one I'm missing. And now it's right here in my directory. And I think you should have it if you downloaded the Google file. And if I just go to it, then I have, it's just a text file, normal Python script. Reduce is the one here that I can edit. If I wanted to make changes to make sky flat, I would go to the next one. This is a recipe library. There are more than one recipes. And if I wanted to add see the intermediate output after the flat correct, what I do is write outputs. That's the name of the primitive. Write outputs. Convenient name. Let's say after the sky correction, write outputs. And they will be given the suffix associated with the primitives just before them. So I think after this one, it's either memory underscore sky corrected or underscore sky subtracted. So something like that. So it should give you, and the top one would be underscore flat corrected. So it gives you an idea which one is which. So that's how I would do it. Now, I'd like you to do a little exercise, edit the recipe, this time we're gonna edit the flat recipe. Let's say I want to see the output just before the normalization. The output of I'm reducing flats, and for some reason I want to see the output just before the normalization. So how would you do that? So maybe in the interest of time, I'll go. I'll just demo it to you. So I would do first. I need a flat. So let's find myself some flat. This one is a flat. Show recipes. This one. That's the location. That's the name of the recipe library. I'm going to copy it over. My nearly flat recipes. And then I go very flat recipes. Make process flat, and the same deal. Just go, whoops. Oh. To write outputs. And then I'd be able to run that. Now, how do you run this? Here you have the syntax. It's basically -r again. -r is your friend. Now you need to provide the name of the file that you've just edited. And then it's the name of the recipe that you want to run. So in my make process flat recipe, I would do reduce flats. Yes, I'm gonna move on. -r my nearly flat dot make process flat. Process flat. And that's how it will know to not go try to find a recipe. It will just use the one that you've specified here. And I'm completely run out of time. Have a look at the final one. This is the really fun one. But it's not very complicated, but it's something you can have fun with. It introduced 3 tools, type walk. We use the tags. Well, you need to know which tags are available. Well, type walk will basically go through all your files and list all the tags for each one of your files. So that is useful when you want to try to figure out which one's which and which one you can use. Show D is for descriptors, and you will see that the descriptors, the names are very descriptive. If you go, you have links in there that will lead you to the list of the of descriptors. And let's say I want the exposure time. Well, I'll go to the list, and it's exposure underscore time, filter name, filter underscore name, UT date, UT underscore date. So you shouldn't have too much problem figuring out what you want to, the name of what you want to look at. And then with that, you can just basically show -d, the name of descriptors, and it will just list a nice table. Let me just. Here's an example. If I want to see the exposure time, filter name, UT date for all the files, it will list me a nice table with all the information. So that's useful again when you use the data select next. And here I have several examples for the data select that will use the tags, the expressions, and it is possible in the expressions, it's possible to use the and or, it's all Python syntax. And that's your take-home exercise, this one. It's not super realistic, but it will really exercise the data select features. And I'll stop here. Sorry, it was a bit rushed, but I hope that you have the chance to go back and do it at your own pace. You have everything you need, including all the solutions. So we have like technically 3 minutes to answer questions. But frankly, I do have some extra time, maybe another 10 minutes afterwards. I do have another commitment, but personally, I have some extra time to answer questions. And any questions that you put in the Wova hat, don't despair, I will go and answer them all.
Okay, Kathleen, so can you see the questions in the Wova Q&A for you, or would you like me to read them?
Yes, no, I see them. would be tough for you to read the second one, the essay warning.
That's why I was checking.
This one, the essay warning relationship, this file, I have no idea what this is. And maybe I'll get in touch. Yeah, I've never ever seen something like that. I think there's something really wrong with your installation of the Dragon's environment. I think it's related to, I'm not sure, I'm really not sure, but I think it's related to some SQL package or some database. There's something odd going on here. CalDB init database is not configured as standalone. That's probably because your standalone was set to false. Usually that's the problem. Another problem that I've seen with the init or when the Cal database is if the directory that you specify, it must exist. If it doesn't exist, I think in the public version, it just will keep continuing very happily, but will be really, really messed up. We've faced that one like less than a month ago, so we went on and fixed things a bit to make it a bit clearer. But that's something that we saw. So standalone. Is it Caleb's? Yeah, that's. So those are debugging questions, and I will go back and try to figure out and help you out with these things. Any other questions? So I see that there were a few votes. So that the CalDB won. If you have few vote, that means that a few of you did get this problem. So keep an eye on it, and I will, if not before my other engagement, later on tonight or tomorrow, I'll answer the technical questions that you have there. We'll try to figure it out. Anything else? And by the way, I would really like to get your feedback on this. This is a brand new workshop. Very first time I gave it. Nobody else got that one before. So you were my test participants. Thank you very much. And if you can share your feedback, it will be very useful for the next group I present to. Oh,
I'll just come on and say thank you, Kathleen. Thanks everybody for coming. And it's been a great workshop, and it's been a great meeting for those of you who are still here. So, and have a good day, afternoon, evening, wherever you are.
And have fun with dragons, and keep an eye out for the next release. The GMOS spectroscopy stuff is really cool.
Awesome.
Thank you, everyone. Bye-bye.
Bye.